calendar. Yes.
We are having the exam on the 6th?
I don't know. We'll talk about that next week. You understand? We'll talk about, once we finish the lectures, we'll talk about the exam. Because Norman, what happens if I get sick? What happens if I go for my COVID shot and I can't get up that day?
Sir, I'll give the class. Don't worry.
Thank you, Omar. I appreciate that. You know what I can do if I do get sick, I could take my video from last year and just send you the video.
Yeah.
Because I do have all last year's classes videoed also, you understand? So if you do want. But okay. Okay, so let's get started. And today, oh, sorry about this. I should have closed this way back when. Okay.
You didn't post it, right?
No, not yet. No, I'm sorry. I was about to, but then I got involved. I got involved because Mark Bernardi sent me the email for the job, and I wrote back to him, and he wrote back to me. So I kind of got caught up on that, and I figured, I'll do it after the class. How's
for
that?
This
Okay.
person that is looking for somebody for the summer, does he speak mainly English or French? Like
he doesn't care if you speak English or French. He just wants to make sure you have a vehicle.
Okay, great.
Okay.
I sent you a message, by the way.
Okay, so in other words, so if you're interested, Rena, just send me an email to my Dawson website, and I will give you a and everything else. Okay, and what he wants you to do is send him your CV. Okay, tell him what you've done. Okay, and of course, stress on the environmental thing that you've done. You know, if you're applying for an environmental job, you know. So, because guys, in theory, your CV should not change. It should be the same for all jobs. It's only your cover letter that might emphasize more on the areas where the company is looking for a certain specialty. And that's where you would, you know, further your CV in the cover letter. I don't know if they explained that to you in your other courses, but that's what you should be doing. Your CV should be the same. I haven't changed my CV for over, over 30 years, you understand? And whenever, like, so just to let you know that the CVs are basically, you change them when you change your jobs because you can go into a new employer. But if you're staying with the same employer, your CV should not change. And it's only when you apply for a job that you have to elaborate, you know, in your cover letter, where you have to try to make them understand that you do have the expertise to do what they're looking for in the job requirements. Anyways, okay, this is being recorded, right? Because I can't see anything right here. So
yeah, it is.
Okay, thank you. So okay, so today we're going to talk about nails and spikes. Okay, and I guess you all know what nails are, right? But nobody knows what a spike is, right?
Yeah, not really.
Not really. Okay, so don't worry about it. Okay, and then after that, I'll show you all the other type of connections that you have that in order to connect, you know, to fasten your lumbers and do your connections.
I might know what spikes are. They are the piece of metal that you attach on. They have like their surfaces are like small nails, like and then they kind of like hammer them on the beam.
Well, yeah, like, and nails are hammered onto the beam also. So both nails.
I know, but yeah, but this is kind of a sheet or something.
Well, okay, well, I'll show you what spikes are. Well, I'm talking about, like, don't think of, guys, don't confuse this with railroad spikes. Okay, that's a completely different spike. I don't know if you guys know about railroad spikes. That's a spike also, and the railroad spike is a very, very specific spike because it's done so in such a way to be able to hold the rail in place when it's being nailed into the tie. You understand? So that's a different type of spike. I'm talking about for wood lumber. Okay. So here I'm going to show you pictures, so this way you'll be able to visualize this. Okay, let me go back. Okay, so guys, these are of course nails, right? In other words, these are what we call common nails. Okay. And of course, there's a head and there's a point and all that, okay? And the nails come in different lengths. And, you know, I don't know if you guys know this, but, you know, you can have nails starting at 1.5 inches, 2 inches, 2.5 inches. And they also have these I never learned this, by the way, guys. So I never specify nail, for example. I never specify a 3-inch nail with size D, you know? So I always specify the length of the nail. Okay, so if I want the guy to put 3.5-inch nails, I put a 3.5-inch common nail. Okay, and I want to specify common nail because today with the pneumatic hammers, they're also 3.5 inches, but the diameter is slightly smaller, and therefore it won't have the same resistance. And when they do that, what I tell them to do is increase the number of nails in proportion to the reduction in diameter. So keep that in mind. So these are, like I said, and of course, these are nails that are fabricated from a piece of wire. Okay, so keep in mind, like I said, you can go up to 6 inches. In like when you're framing, like today, a lot of people are using screws, you know, as opposed to using nails, but nails are still being used. And of course, a lot of them are being used with pneumatic hammers. Okay, so usually when you're framing, like in the old days, when you would be framing a house or a building, okay, the most common nail you would use is 3.5 inch in length, okay, to fasten the lumber together, and then the one to fasten the sheeting to whatever you're, like, in other words, your plywood, whether it's the flooring, whether it was the wall sheeting, whether it was the sheeting on the roof, the most common nail that they would use there was 2.5 inch. So the carpenter would most likely have 2.5 inch and 3.5 inch. That was the most common nail that they had. Very rarely did they have 4-inch nails, okay? And so on, because that extra penetration won't necessarily give you any more resistance and so on. So that was the most common size that, okay? And now today, of course, with the pneumatic hammers, okay, it's a whole new ballpark. And as a matter of fact, I know one carpenter, he likes to screw everything. So he's got this, you know, he's got this cordless screw and he screws everything. And he's probably just as fast as the guy that's nailing with a pneumatic hammer with his screw gun, understand? And that's how he fastens things. I like his way of doing it because it's a much better fastener. So just to let you know, so these are the you know, common nails, and that's what I want you to understand. Common nails. So when you're referring to the common nails, it's a regular head, you know, and so on. Now these are spiral nails. Okay, so in other words, they basically are very similar to a common nail, but they are twisted. Okay, and of course, where are these nails made from? Well, they're made from pieces of wire rope. Okay, so in other words, this rope goes through a machine and the machine literally stamps these things out. I don't know how many thousands per minute that the machine does, but they're all made from wire rope. So the machine actually takes a piece of rope and bangs it out so that it creates the head and it creates the point all at the same time, and then it spews it out and they package it and they sell it. Okay, so the spiral nails are also used. Okay, and you'll see the advantage of the spiral nail over the common nail. So now these are spikes. Okay, so spikes are basically, they look like nails, but they are much, much bigger. Okay, and on top of that, they're not made from wire rope. These things are actually cast. Okay, they have to cast these things in a form. Okay, and of course, these things are so big that you should pre-drill your timber or your lumber before you drive it into the wood, because if you don't, you have a good chance that you're going to split your wood. Okay, so therefore, whenever you're using these thicker you know, fastening elements to, you know, hold these big pieces of timber together, it's always recommended that you pre-drill a hole. What size? They recommend 75%. I like to use 50%. Okay, so they recommend 75% of the diameter of the hole to be drilled before you drive the spike in. And I wouldn't go over 75. Okay, so anywhere between 50 and 75 is a good diameter pre-drilled hole, and then you actually drive the spike into the hole. And of course, so this is a spike, and like I said, these things are cast. And if ever you take a 4-inch spike and a 4-inch nail, the spike is a little lighter. You'll feel that. You can feel it. And then on top of that, you'll feel that the spike has been cast. It's not the same steel or the same metal as the 4-inch nail, because the spikes start at 4 inches and then they move up all the way up to 14 inches, whereas the nails start at 1.5 inches or even smaller. But for construction purposes, for all practical reasons, let's say 2 inches, and then they move up to 6 inches. So, and that's a spike. It looks very much like a nail, like I said. It is used to fasten big pieces of timber together, okay? And, you know, so now common nails and spiral nails are used for general construction, which makes sense, okay? Spiral nails have greater withdrawal resistance than common nails and reduce splitting. So what this means is that if you want the nail to be able to have a stronger resistance when it comes to, does everybody understand the word withdrawal? In other words, if the nail wants to get pulled back out of the piece that is being fastened to, the spiral nail has a greater withdrawal resistance, okay? And at the same time, it reduces splitting, okay? So that's the other advantage of using spiral nails. Some carpenters do use spiral nails. Some people just use common nails, okay? Spikes are longer and thicker than nails and are generally used to fasten very heavy pieces of timber, as you saw before. In other words, if you're building a retaining wall out of that timber and you want to fasten the timber together, well, one of the things that you might want to consider using are spikes, and then I'll show you there are other options later on to fasten timber in that fashion. Now, nails are available from lengths from a 1/2 inch all the way to 6 inch, okay? So that's the length that you can get them in, okay? So that's the common nails. And of course, spikes go from 4 inches all the way to 14 inches. So that's a nice length, okay? That's pretty long. So that's what they come in. And if you ever need a 14-inch spike for whatever reason, well, you know that it's available. Okay? I don't know how available it is, but at least they do make some. Now, as far as when you're designing something, that was just to give you an overview on nice, spikes and nails. Okay, so you know that whenever you are designing anything, you want to know the factor lateral resistance is greater than the factor lateral force. So in other words, what that means is very simple to me, okay? So here, if this is my piece of wood here, okay, and here's my other piece of wood here, okay, and all of a sudden, this piece of wood is being pulled here, and this piece of wood is being pulled here, and I decide to, let me just put in a nice, I should put it in blue. I like blue steel. And I decide to put a nail in here to fasten these two together, okay? So what happens is, as this thing pulls here, okay, it creates, as you've seen in steel, right? As that thing pulls there, where's the color? Okay, it's going to be pushing here on the nail, and the nail is going to have to be able, the wood that's here has to be able to resist that pushing all along there. And when it's being pulled there, the same thing here. So it has to be, so therefore, whatever resistance the wood has here and whatever resistance the wood has here, okay, the sum of all of that, if you need 18 nails, the sum of all those 18 nails should be greater than the force that you're trying to resist. And that's what you're actually trying to do, okay? So that's, that's basically, it's very similar to bolts, except now you are definitely relying on the wood to be able to determine how strong is it going to be in bearing as the wood pushes against that nail. When is that wood going to start crumbling and failing because you've exceeded the resistance? And that's what you're actually doing. And of course, where in steel, you worry also about the shearing of the bolt because steel is very strong, but normally you don't worry about the shearing of the nail itself because normally this is much weaker than the shearing of the nail. Okay, so you don't even consider that. So that's what you're doing. Oh, I'm sorry.
Sir, are screws are they how do you call that? Oh my god, I'm so sorry, I forgot the word. Hold on.
Go ahead.
Oh yeah, do screws have less shear resistance than nails?
Let me finish the lecture, Rena. Okay. I will talk about screws very quickly. In the handbook, I have, for example, I have the resistance of screws if you plan to use screws, okay? But then on top of that, I'm going to talk about lag screws, which is even another type of screw that is more common to use. So let's finish the lecture, and then I'll let you know that which one. Like in other words, it depends. Are we talking about withdrawal? In other words, the nail being pulled out of the joint, or are we talking about the nail getting pushed against the screw or the nail? Okay.
Okay.
So what you have to remember, Rena, is that if it's withdrawal, of course, the screw will have a better withdrawal resistance than a nail because it actually, spirals into the wood. Okay. But then in terms of the lateral resistance, it all depends on the diameter of the screw and the diameter of the wood, of the nail. because it's a surface area that comes in contact with the wood that's going to determine the resistance.
Okay, yeah.
You understand? So if you see that, then you'll understand that, okay, it's just a question of I need more resistance, I need bigger diameters, okay, in terms of pushing against the screw. If it's being pulled out of the wood, then I need better withdrawal resistance, okay? And if you want to know for screws, I'll be more than happy. I can copy the pages in the book, and I can just send them to you. You understand? So you don't have to buy the book. So
Okay, thank you so much.
okay, so now the factor lateral resistance for a load at any angle to the grain is calculated by the following formula, okay? So this is the formula. So NR is equal to NR prime, NS is the number of shear planes, NF is the number of nails, K is, of course, K factors when it comes to the environment that the nail is in, and we'll talk about all of these, okay? So now, NR prime NS, basic factor lateral resistance given in the nail section tables. Now, I know that this is going to be a little bit overwhelming, but don't worry, okay? So this is what you have, and I'm going to be providing this with you, okay? So here, let me go back to the very first page, okay? So this is where you get the value of NR prime NS. In other words, the values of NR prime NS are right here, depending on the species that you are fastening, okay? So if you're fastening SPF, you would come here. If you're fastening northern lumber, you would come here. Now, if you're fastening Douglas fir and SPF, you always take the weaker of the two, okay? Now, the way that the table is made is that it is very, very confusing sometimes, but all of this are the values based on a minimum penetration. Okay, so in other words, this is the minimum penetration that the nail has to go into your joint. Okay, now if you don't have 16, well, you can't use the table. You can't prorate to less than 16. You have to have at least 16 millimeters penetration in a Douglas fir if the lumber is going to, and if the side, now, what the side plates are, let me explain this also, okay? So basically, the side plates means this, okay? If I take a piece of lumber here like this in plan view, and I take a piece of lumber here like this in plan view, okay? And if I plan to, fasten these two together with nails like this, okay? Well, what am I fastening? I am fastening, let me just find, okay. So what am I fastening? I am fastening lumber with lumber, okay? And therefore, if I wanted to know the resistance of these nails that I'm using to accomplish this connection here, I am then looking here. The side plate is made out of saw lumber, and you'll notice that it's only for lumber that is 38 millimeters thick. So it doesn't matter if it's a 2x4, a 2x6, a 2x8, a 2x10, or a 2x12, as long as it's a 2 by something, because you won't go fasten a 4x4 with nails. It starts to be too long, okay? So basically, if you're fastening lumber to lumber, then you would use this table here. So because here your side plate is lumber to lumber, okay? And therefore, so this is where you would come and get the values of NR prime for, now, like I said, this table tells you what you need as a minimum penetration. And this table tells you what you need. This tells you okay, what is your maximum penetration? Okay, now, for example, if I take a piece of lumber here like this, okay, and I have another piece of lumber here, okay, and all of a sudden I am driving a nail here like this, okay, through here like this, and I'm driving it through there, and this of course is 38 millimeters, right? So right now what's happening is that this one you don't worry about. You worry about the member that you're connecting to it. So therefore here, your minimum penetration, they say that you need for this, if it's SPF, is 16 millimeters. Yes, I have the minimum penetration. And the maximum penetration for SPF, if I'm using a 2-inch nail, okay, if that's a 2-inch nail, is 26. So therefore, I have the maximum. So what they're saying is that this here will not account for anything after that. Okay, so that means that even though you're penetrating all the way through the lumber, they will only rely on the values up to that maximum. So if you happen to have 38 millimeters of penetration, you cannot increase that number. You stop at the maximum penetration. And if for whatever reason your nail happens to go between the minimum and the maximum, between, you understand, in other words, it doesn't happen to be going right through, you have the minimum here, but you don't have the maximum, then you can prorate the values between the minimum and the value to get the values of M and R prime, okay? So the way the tables are set up is that at first you have to look at what kind of side plates you're using to make your connection. So this is lumber to lumber. And then after that, you have to look at what am I using? Am I using common wire nails? Am I using spikes, or am I using spiral nails? That's number 2. So that's the other thing you have to decide. Am I using common nails, common spikes, or spiral nails? And then number 3, what's the length of the nail that I'm going to be using? 2.5 inches, 3 inches, 3.5 inches, and so on. So this is the length of the nail. Then depending on this, now what I like about this table is that it tells you for a 2-inch nail, this is the diameter that the 2-inch nail will have, this diameter is 3-inch nail. So this information is good to know because it's useful, okay? And therefore, once you've decided on what your side plates are, once you decided what type, which one you're going to be using, and then of course what length of nail you're going to be using. So if I decide to use, for example, here, the common thing would be if this happens to be a 2x4, which is 1.5 inches here and 1.5 inches there, well, I know that the maximum I will use nails, unless I want to clinch them, and we'll talk about clinching, okay? Unless I want to clinch them, then the maximum nail I would use to fasten these two together without clinching, and I'll talk about clinching, would be a 3-inch nail, and therefore I would come here and look at the values for a 3-inch nail, okay? So that's, let me just clear this. Now, so that's if your side plates are lumber. Now, if you decide to have your side plates made out of Douglas fir, in other words, this is plywood now, okay? But it's got to be Douglas fir plywood, not just Canadian softwood plywood. Most of the plywood that you see in the stores is Canadian softwood plywood. If you go to BC, most of it is going to be Douglas fir plywood, okay? So the side plate here is made out of Douglas fir. So if you can't find any Douglas fir, you don't even use this table. So what this means is that I'm going to, okay, so I have a piece of lumber here. I have a piece of lumber here. So these are the 2 pieces of lumber. And what I'm going to be doing is I am going to be taking a piece of Douglas fir here as a side plate like this, okay? In other words, I'm going to use a 1/2 inch plywood. I'll take another piece of Douglas fir here. These are my side plates. And then after that, I'm going to be driving my nails to make this connection. And that's, of course, the type of connection you're going to be doing for the truss, because trusses are all made with plywood gusset plates. But you're not going to use this table here because we're not going to be using Douglas fir plywood. So this is only good for Douglas fir plywood. And of course, again, 2.5. So once you decided what side plates you're going to be using and what type of material. Now, don't get confused, guys. I've seen this year after year, okay? Don't get confused. This here is for the side plate. This here is the lumber that you're fastening. So it can be Douglas fir, but this is the lumber that you're fastening. So in other words, if I take a piece of Douglas fir here, this is Douglas fir here, and I take a piece of SPF here, and then I decide to use Douglas fir, I decide to use Douglas fir side plates, well, believe it or not, what I need to do is I need to go and take the values of the weaker. So therefore, I would look at, for example, the weaker of the 2. So in other words, I would look at this one here and this one here. And of course, this is the weaker one. And that's the one that I would always base on the weaker one, okay? So if you're using different species of lumber, always take the weaker lumber. That's for sure. Because if you take the stronger one, this one can fail on you, and your joint's going to fail and everything's going to fall. So that's if your side plates are made out of Douglas fir. And again, minimum penetration, maximum penetration. And this is penetration in the member that you're connecting, okay? So keep that in mind. Now, hopefully through an example, this will, okay. After that, you have also side plates made out of plywood. This is Canadian softwood plywood. And this is most of the plywoods that you're going to see in the lumber yards in Quebec. Okay, it's all made with Canadian softwood plywood. In other words, this is made with either spruce, it could be made with fir, it can be made with pine. They're all Canadian softwood plywoods. They're all basically the same, okay? SPF has about the same value, and when they make the plywood with it, it has about the same resistance, so they put that all into one category of plywood. So this is, for example, where you would come for, if you'd be designing your gusset plates for your truss at home, and we're gonna use the same one for our project, this is where you would come and get the values of N prime R and S. Okay, NS is a number of shear planes, and we'll talk about that. So this is for, and of course, again, this is to assure that you have a minimum penetration and this is the maximum penetration. I hate how they revamped nails in the handbook, okay? As a matter of fact, guys, I can tell you that it's scary because with the new way of calculating nails, half the projects I've done in the past, the nailing would be insufficient according to this new way of doing it, okay? Just to let you know how things can change. And if something happens to whatever I've done in the past, I can't go back to, well, that's what was done at the time and that's how I calculated. And it's scary. When I saw this revamping of the nailing schedule, I've modified a couple of trusses and I'm happy it hasn't failed yet, okay? And that's why I keep telling you guys, always put a little bit more than a little bit less. It won't hurt at the end of the day, okay? Especially if they revamp. Again, this was like something that was really scary for me when I saw this, when they came out with the new handbook, and this is the way that you calculate the resistance for nails. As a matter of fact, in the handbook, they took the same example, and what they did is that they reduced the force that the members were being subjected to just to show that they got the same number of nails as the previous handbook. And I thought that that was very, very deceiving. I almost felt like writing them a letter saying, who are you guys trying to fool? Understand? And that was very, very deceiving, I found. So this is for Canadian softwood plywood. CPS stands for Canadian softwood plywood. And of course, you can have a 1/2-inch plywood, then you can have a 3/4-inch plywood, and of course, you can have 7/8-inch plywood, okay? And of course, as the nail gets bigger, they recommend that the thickness of these side plates also get thicker, okay? Otherwise, you're really not taking advantage of the fact that you're using a bigger diameter here. So keep that in mind. So if you want to use 6-inch nails, remember your side plate, they recommend that you use 22.5 millimeters in order to use the values here in the table, okay? So that's where we're going to come back and of course, get our values for our project. Now, they keep going. Now you have, if you happen to be using OSB, and of course, you guys should remember what OSB stands for, Oriented Strand Board. Well, Oriented Strand Board, of course, won't have the same resistance as plywood, and therefore, okay, so if ever you decide to use OSB, 11 millimeters, 15 millimeters, 18 millimeters, 22 millimeters, this is where you come and get the values for the OSB if they are the side plates. So a lot of people like to use OSB because it's a little bit cheaper to buy than plywood. That's their choice, okay? And of course, if you're going to be using OSB to do your gusset plates, well, this is what you do to come and find your value of, okay? And then you can also have what they call light gauge steel, but it's got to be 20 gauge. If you guys remember when we did way back when we did the steel deck for the steel project, they talked in gauges. They talked about 20, like 22 gauge, 20 gauge, 18 gauge, 16 gauge. Well, here they want you to use at least a 20 gauge steel. Okay, so in other words, that has to be the thickness of the sheet metal. And if you want to know how many millimeters the 20 gauge is, okay, you have it right there. So a 20 gauge steel has a thickness of 0.91 millimeters. In other words, this is the thickness for a 20 gauge steel. And therefore, if you happen to use sheet metal and you want to use sheet metal, you're more than welcome to do it. And then this way you come and get the values of, okay, because you can appreciate the bearing of the nail on sheet metal is going to be a little bit stronger than the bearing of the nail on wood. So therefore, that's why you have, like, some people might want to go with sheet metal and decide to go that way to make their joint. Now, so that's for sheet metal. And then ultimately, okay, then they also have it for 14 gauge. In other words, 14 gauge, the thing that's ironic about gauge measurement is that as the number gets smaller, the thickness gets bigger. So this is 1.9 millimeters. And I'm not sure, I'm pretty sure that I've never done this before, but if you happen to have, if you want to use like a 16 gauge, I'm pretty sure you can interpolate between the two, because as far as the steel goes, if you interpolate between the two, I'm pretty sure that the steel is going to have the same resistance and bearing. I've never had to do it, but I'm not going to say that categorically that's the way to do it, but I'm pretty sure you can interpolate between a 14 and a 20 if you happen to have a 16 gauge steel. So that's okay. Unless now, ultimately, okay, if you can also use steel plates, okay, and of course here this is a 1/4 inch steel plate. Okay, this would be the ultimate. Okay, so for example, when you're fastening, like heavy stuff, and you want to use so if you're fastening, if you're using steel plates with a thickness, and of course this is a very A36 steel is not very, very strong. So they're taking the weakest steel. So for example, if you happen to be using, our steel that we're always been using, the steel, in other words, the if you happen to get the plates that are made with the A992 steel or whatever, you know that it's going to be more than ample, because this is one of the weaker steels that is produced. Okay, A36 is one of the weaker steel, or the one that has one of the lowest yield points. And therefore, for a 1/4 inch thickness here, same thing. So you can use steel plates to do your connections. Okay, so this is, but like I said, it's, the most common thing to do is, like, the most common joints you have, of course, is either going to be you're trying to join lumber with lumber because you want to splice them together to do something with lumber to lumber, or you're going to make gusset plates in a truss with the plywood, because you're going to want to be able to, make your own trusses at home. And therefore, instead of using Douglas fir for your side plates, if you can find Douglas fir, because if you find that this is going to be beneficial for you, and you want to spend more, it's available in Quebec. Don't get me wrong. You can find Douglas fir plywood in Quebec. More expensive, but if with a little bit more resistance, for example, here, if we take here, for example, for a 1/2 inch SPF, okay, with a maximum penetration, so you get 5.67. This is kilonewtons, okay, of resistance per nail. That's what this is, kilonewtons per nail. And if I go look at the CPS, Canadian CSP, I should say. If I go look at the next one, so that's 5.6. If I look at here, I get 5.16. So there's a slight, you get a slightly better resistance with the Douglas fir, but is it really going to make that much of a difference? Because it could just be a question of making your gusset plate a little bit longer and adding 2 more nails, okay? And you're going to save and be able to find the plywood for sure and save some money, at least on the plywood. Okay, so that's the table. We will come back to this table and we'll be using it to do our examples, and we're going to be using it also in the lab to do our truss and so on. So, and oh, does anybody have any questions before I go away from this table? I apologize. Just to give you a good overview of what the tables are all about, okay? Okay, so now, next, NS is the effective number of shear planes. Just like in steel, okay, how many planes go across your nail? Of course, if it goes across only on one place, then you have 1 shear plane. If you go across 2 places, you have 2 shear planes, okay? Now, in the old days, this was much simpler. Now they made it really complicated. Well, complicated. It's like, this is one of the things that threw everything out of whack, okay? The nail penetration for shear plane. So now if you want to have a shear plane, it is based on the penetration of the nail. And if you don't have that penetration, even though it looks like you have 2 shear planes, you shouldn't be considering 2 shear planes. And I find that, Now, the minimum required penetration for single shear plane. So if you want to consider that you have 1 single shear plane, this is what you have to do, okay? For side members with the nail head, okay? So remember, it's got 2 different values, okay? Okay, so for example, here's one member, okay? And here's another member. So let's look at this, okay? Here's one member, here's another member, okay? So remember, there's 2 different criteria based on, where is that? Oh, sorry. Okay, so here's my nail, okay? Fair enough. Now, keep in mind that this is the side, okay, of the nail head. So if the nail head is here, okay, the amount of penetration you need to have here has to be 3 times the nail diameter. So if you want to know the nail diameter, that's in the table that I just showed you, okay? Okay. And 0.9 millimeters for steel members. So in other words, if you're joining wood, it has to have at least 3 nail diameters here of penetration. So that means if I'm using a piece of plywood here, and if that plywood happens to be 1/8 of an inch thick, and I want to join that, well, I can't even consider that to be one shear plane. That's what they're trying to make you understand. So on the nail head, it has to be at least 3 nail diameters penetrating into whatever you're joining. And then on top of that, 5 nail diameters on the side of the nail point. And on this side, it has to penetrate at least 5 diameters. And if you don't have that, we're going to be doing this in the problem, so don't worry. So if you don't have at least 5 diameters here, if you don't have at least 5 diameters of penetration here, then you can't even consider that to be a shear plane. Okay, so that means that, for example, if I happen to have here a piece of plywood like this, and I happen to go through that plywood, I want to use plywood to continue my joint and all that. And if this plywood here does not have the thickness of 5 times the nail diameter, if that's where the head of the nail is, then I cannot consider that to be a shear plane. I would only have to be able to consider that to be one shear plane. And like I said, and this is a whole new way of determining the number of shear planes. Now, so that's how you determine the number of shear planes. And first of all, to even consider if you have a shear plane, you have to have at least 3 nail diameters on one side, on the head side, and at least 5 nail diameters on the other side to even consider to have a shear plane. And if you don't have that, then you've got a problem. And of course, and if it's for steel, they just give you the amount of the minimum penetration. Now, the nail penetration for shear planes. Okay, minimum required penetration for double shear plane. Okay, now 3 nail diameters for the member with the nail head, 8 nail diameters for the center member, and 5 nail diameters for the member with the point. So this means that if I happen to have, okay, let me just change, what color should I make the wood? Brown. Brown is a good color for wood. Okay, so here, if this here happens to be one piece of lumber, this here happens to be another piece of lumber, okay? And then all of a sudden I decide I want to use, these are my side plates here. Okay, this is my side plate here. This is my side plate there, okay? So if I'm driving nails, for example, this is in the old days. This is what we used to do, okay? In the old days, just to show you, okay? Very simple. In the old days, what we used to do is very simple. We used to say, we know that this was 1.5 inches. We would have 1/2 inch plywood, 1/2 inch plywood. We would have 1/2 inch plywood, okay? And therefore, if I would take a 2.5 inch nail, in the old days, I would consider to have 2 shear planes, okay? That's the old days. Now, what happens is that if this plywood here does not have 5 times the diameter for the thickness, I cannot consider that to be a shear plane. Okay, and that's what the problem is. Okay, so in other words, here I have to have, this has to penetrate at least 3 diameters of the nail. Here it has to penetrate at least 8 diameters of the nail. Well, here's not a problem because I know 8 times, like for example, even if I have a 3 millimeter nail, that's 24 millimeters, and this is going to be 38 millimeters, not a problem. So this has to be at least 8 times the nail diameter at the center and 5 times the nail diameter at the point. Okay. So keep that in mind. Before you jump to 2 shear planes, make sure that you meet these criteria. So that's, where is that? Clear the drawing. Okay, so now, NF, of course, is the number of nails or spike. I'm continuing with the equation, okay? K prime JF, okay? So this is gonna be fun, guys. Well, K is simply all the K factors lumped into one K prime value, okay? Where, for example, K prime is KD, KSF, and F is for fastening. Of course, that's why they put an F, but it's for serviceability, wet or dry. And KT, of course, is the wood treated or not. So here what they've done is they've taken all 3 of these and said, Well, depending on your KD value, depending on your serviceability, what environment it's in, depending if it's treated, well, you multiply all those three together and you just come up with one value here, just stick it into your equation. Now, of course, KD you're very familiar with, okay? Hopefully you are. So if it's a standard low duration, KD always stays 1. If it's a long-term or permanent for the short term, for example, if you're designing for wind, in other words, you're doing diaphragms, wind and whatever, or you're doing formwork short-term, then you can take KD equal to 1.15. And if it's a permanent load, in other words, very long-term, you take KD equal to 6.5. So the KD values have never changed. Okay, they've always stayed the same value. Okay, it all depends on the duration of the load. Now, KS for serviceability, right? If it's dry, of course, it's always 1.0. Now, keep in mind here, 1.0 for service conditions for dry, and the lumber is seasoned. Seasoned wood, does anybody know what seasoned wood is?
Nope.
Seasoned wood means you take a piece of wood and you put some salt and some pepper on it, and that's how you season it, right? The same way you season your steak. Does everybody agree?
No.
No.
No. Okay. So seasoned wood means that, guys, I hope you appreciate, I don't know if you guys ever did this, but has anybody ever cut a plant?
Yeah, of course.
Okay, you've cut a plant. And when you cut the plant, did you ever put your finger where you cut the plant?
Yeah.
Did you feel a lot of moisture?
Yeah.
Okay, because all plants have a lot of moisture. So when trees are cut, they all have that because they're all alive. They're all alive, these trees. So when they're cut, they have a lot of moisture in the wood. Therefore, what you need to do is you need to make sure that the wood eventually releases that moisture from the wood. And therefore, if you want to consider it to be dry, it cannot have more than 15% moisture content. Okay, as a matter of fact, the National Building Code says you cannot frame any house with a moisture content of greater than 19%. Okay, so if your moisture content happens to be greater than 15%, well, you can't consider it to be dry. Okay, now, how do you know if it's seasoned or unseasoned? Well, when you go look at your lumber, okay, on the stamp of the lumber, first of all, it's going to tell you the species, it's going to tell you the grade, and it's going to tell you if it's dry or if it's green. If it's green, then it hasn't been seasoned. Most likely the moisture content is 15%, and therefore you have to take that into account when you're doing your connections, because as it dries, it will shrink and it will add additional stresses to your connection. That's why. Okay, so moisture content. Okay, and then of course you can, I don't know how much they're worth, but they have, did you learn this in your inspection course, that there are meters that you can buy to measure moisture contents of when you're doing your inspection?
Yeah, we learned about it.
Okay, that's it. So that same meter is what you use. You go to your piece of lumber and you go to the job site, you stick it into the wood, and it can tell you what the moisture content is. And if it happens to be over 15, you've got a problem. Okay. So that's number one.
Sir,
Yes.
how is the seasoning done? Is it like air dried, or do they put
There's
it in
two
like
ways.
an oven?
There's two ways. The cheap way, they cut it and they let it dry in the yard.
Okay.
That's number one. So that's called air dried. Okay. The other way is they cut it, they stack it, and then they put in these big kilns. You know what a kiln is?
Yeah, it's like an oven.
It's a big oven, exactly. So they just go in there and they put all the oven, and that's called kiln dry. And on the lumber, you're going to see KD stamped on it, kiln dried. Okay. So it can be kiln dried, and of course that's much faster. And then it can be just air dried. Okay. And if it hasn't been air dried or kiln dried, the guy that produced the lumber has to stamp green on it. So when you see green, pardon?
Is one stronger than the other?
No, it's not question stronger than the other. Well, I mean, yeah, because if it happens to be green, you're going to see you're going to have to reduce this value. You follow what I'm saying?
Okay.
So yes, that's why they're telling you right here, if you're going to be using green wood, as a matter of fact, here, let me just go there, and this way you can see this, okay? So in other words, you'll take your resistance and you're going to take only 80% of it. You see
But in terms of kiln and air dried?
No, because it's got nothing to do. It's just it all depends on moisture content. So you don't care whether you brought that moisture content just by air drying it, over time, or you did it really fast in an oven. As long as the moisture content is between 15%, you don't care how you got there.
Okay, thank you.
Does that make sense?
Yeah, makes sense.
Okay, so that's it. So just worry about how you're going to get the moisture out there and make sure the moisture stays out. Now, guys, when it rains and the wood gets wet, don't worry. That's just very superficial. And then when it stops raining, it dries up again. Okay, you want to get rid of the moisture that's in that whole member. Okay, and make sure that it's less than 15%. Like that 15% that it goes over on the surface, don't worry about that. Eventually, that will go back to what it was supposed to be. Okay, so but like I said, when you look at lumber, and if it happens to be green, okay, so now I shouldn't get into this, but I'll talk about this another time. It's so funny because I had a discussion with another expert on this project, okay, and he was doing his calculations, and he says it's no good because it's green. Look, it's stamped green. And you got to use 0.8. And I said, yeah, it was green when they installed it in the building 20 years ago, but over 20 years and the building's been heated, the moisture content is probably at 8% right now. So therefore that doesn't make sense anymore. Therefore we should use this value here to do the calculation and see if it's okay. And that's why, the difference between understanding what this means and when you should be applying it. You apply this when you're actually designing your joint. But for example, if the joint's been designed and it's been there and it's been seasoned and everything else in the building, you can go back up to this. It's just, this is based on the moisture content, not what you see on the stamp. So for example, just because it says as dry here, and then for whatever reason, the moisture content in the building, it became very humid and it went over 15%. Well, that might have been one of the causes why the joint failed. You understand? So don't, so yeah, you have to worry about moisture content, and that's going to determine which one of these two that you're going to be using. So now, and of course, 0.67 for wet service condition, regardless of seasoning or not. So in other words, if your wood is considered to be wet, in other words, wet normally means, if I'm trying to go by memory, but I think that when your moisture content is over 26%, I think they consider that to be wet wood. Okay. So like less than 15, and I think it can go up to 26 for it to be unseasoned lumber. And then after that, if it goes over 26%, in other words, if your lumber's got 50% moisture, it's wet. Okay, so therefore, this is what you should be using for wet wood. Okay, so you have 3 different values for KSF, and of course, if you're going to be using dry lumber, which is what you're going to be buying anyways, and it's going to stay dry in its environment, then don't worry about that. Your KSF is going to be 1.0. And the treatment, okay? So fire retarding treatment factor, okay? So 1 when the wood is not treated, just like everything else, when it was a joist, so on and so on, okay? Or other strength reducing chemicals. And like I said, when it comes to KT, guys, if the architect wants to treat the wood because he needs a special fire resistance, you tell him who is the producer, or who is a producer of the fire retardant that you're planning to use on the wood, and you call up the manufacturer and they will give you the KT value. They have to, because they would have to establish it by tests, okay? And they will tell you what the KT value. Don't guess it. Don't go take something out of a book. Call the manufacturer, ask them for the KT value. Now, J, okay? So J, there's a lot of things that can affect J, okay? So we'll take them one by one, and hopefully, okay? So J, okay, factor for nailing into end grain, okay? Now, you should realize that, I know, I realize this, but you should realize that, I'll draw it this way, okay? Let me draw it this way, okay? Okay, this is my piece of lumber here, like this, okay? Now, here is the grain of the wood. Everybody understands that? Is that clear to everybody, or is my drawing pretty ugly?
It's good.
It's good, okay. And of course, if you look here, you start seeing all the rings that the wood has, right? And of course, that corresponds, okay. Now, so when you're talking about, okay, you can appreciate that if I drive a nail here into the end grain, it's much weaker than if I knock it here into the side grain, Okay, so depending where in which direction the grain is acting on the nail, you have to take that into account. Okay, so this is for nailing into the end grain. Okay, so I'm not going to clear that because I'm going to use it. So when the nail are used in side grain, in other words, when I take my nail and I drive it right through here, and it's in the side of the wood, therefore the JE is 1.0. And normally, you know, when you're splicing two members together, you're usually always doing side grain to side grain. But if for whatever reason, like for example, you're nailing a plate here to the bottom of this lumber, then you're nailing from the plate into the end grain of the member. And therefore, if you want to calculate the withdrawal of that connection, because you might have uplift, you have to reduce the resistance. Okay, so this is for side. And of course, if it happens to be, and of course, when you happen to nail, so in other words, where do you nail into end grains? Well, it's very simple for me. I mean, it's like, here's a bottom plate, here's a vertical stud, here's my nail. So here I'm nailing into the side grain, and guess where I'm nailing here? Into this member. I'm nailing into the end grain. Okay, so therefore, when I want to calculate the resistance, if I have to calculate, for example, if there's something pulling up and I want to be able to calculate the resistance of this, I have to worry about taking this into account. Okay, so it can, for example, if I happen to have a header joist here and then I have joists coming here, well, when I'm nailing through the header joist into the joist itself, well, this is a side grain here, and of course I'm nailing into the end grain of this joist. So you have it's always going to be based on the weaker of the two. Okay, so that's something else you have to take into consideration. Am I nailing in the end or am I nailing into the side? And look, you lose 2/3 of the resistance when you're nailing into the end, so it's significant. Okay, now JA is for toe nailing. Okay, now who doesn't know what toe nailing is?
I don't, sir.
You don't? Okay. Who? Okay. So that's why I know. So what I did is I'm going to show you what toe nailing is. Okay. This is toe nailing. In other words, you're not nailing on the side. You're not nailing at the end grain. You're actually driving the nail at a diagonal. Okay. So these are toe nails. And of course, if you look here, okay, it can happen, for example, if you want to hold this lumber here to this one, there's no way that you're going to be able to drive a nail through this, and therefore you have no choice but to toe nail here. Like if you're putting this blocking to build up your structure, well, this piece of wood here, you can nail this way and hold it in place. But then when you put this piece, how are you going to be able to nail it this way? Well, you got no choice but to toe nail. Okay, so these are all situations where, and of course, if you're building your partition and your plate is already on the floor, okay, and you need to, you know, nail your studs to your bottom plate. In other words, if you don't have this luxury of having your bottom plate like this and like this, okay, and everything's laying flat on the floor and that you can nail underneath here to hold everything together, well, if that's not, if you don't have that luxury, you got no choice but to toe nail to hold the stud to your bottom plate. Okay, and that's what they're showing you here. Now, toe nail means what? Toe nail means that you're driving the nail at approximately 30 degrees. Okay, now not 45, not 25, approximately 30 degrees. Now, you don't go out there with a set square at 30 degrees and tell the carpenter, wait, let me measure your angle. Trust me. Okay, they know what to do. So here, what they're trying to show you is that this is one option. You could toe nail. Okay. Now, if that's not strong enough, of course, you can always put we'll look at these mechanical fasteners, okay, to tie it down. Now, here, what they're trying to show you is that if I have a beam here, okay, and the guy is putting his joists, and the joists are side loaded on the beam, okay, the carpenters always do this. They will not put all the joists first, and then they'll come and put the joist hangers first. What the carpenters will always do, okay, is that they will toe nail temporarily the joists in place, toe nail them temporarily, so that they hold there as they're framing the floor, whatever. So they will toe nail temporarily, and then they'll put the plywood down. And then after, before the drywall goes up and everything else, they'll come and at each joist, they will install the joist hanger, okay? So that's how it's done, okay? Because this way they know that when they put the joist hanger, because he wants to make sure that the top of this joist here is always in line with the beam and all that, and therefore, because the lumbers aren't all exactly the same size, they don't care if it doesn't meet here exactly, but as long as, so therefore the carpenter will always make toenail the joist to the beam, temporarily hold it, and then before, of course, before he leaves, you're going to tell him, well, go back now and put your joist hangers to finish the job. Okay, so this is a temporary toe nailing, and then this is the permanent thing that's your and if you want to be really conscientious, you can actually calculate what these give you, and then I can minimize the size of joist hanger that you need if you want to do that, or you just don't even bother, you just calculate the joist hanger and that's it. Okay, so this is toe nailing. Okay, and like I said, there are situations where you have no choice but to toe nail, okay? And especially in this situation here, if you need to hold your stud onto a plate, you have no choice, especially if this plate has already been fastened to the floor. So therefore you have no choice, okay? And of course they put 2 on one side and then the other one goes right in between the 2 on the other side. That's what they're trying to show you here. 1, 2 there and 1 on that side. You don't put like 2 on the same side and 2 on the other side. It's 1, 2 on one side, 1 on the other side for a 2x4. If it happens to be a 2x6, well, you can go a little bit wider. Okay, so that's toe nailing, and I hope that that gives you a good idea of what we're talking about. Okay, now 1.0 when the nails are not used as toenails. Okay, that makes sense. In other words, you don't no reduction factor. But if you are, you have to multiply the resistance that you have by 0.83 for the toenail, provided that the nail is started at approximately 1/3 of the nail length from the end of the piece. So this means that if I'm going to, here's my piece of lumber. Okay, here's my piece of lumber. And this is what I want to toenail here, okay? So in other words, this here, I have to start at approximately, okay, 1/3 the length of the nail from the end piece. So in other words, if I have a 3-inch nail, I have to start at 1 inch here, approximately, okay? And at an angle of 30 degrees to the grain, okay? So that's what they, and guys, seasoned carpenters, they know this. First of all, they learned this in their trade school, okay? And trust me, these guys are good, okay? So they'll I mean, it's gonna be 30 degrees. Like they know, like they have their nail in their finger and they know exactly like to drive it in and how far and so on and so on, okay? Because if you put it too close, it's gonna split the wood, and if you put it too far, you won't have enough penetration, okay? So keep that in mind. So that's what you need to do. So when you see the guy toenailing, if you see that he's using a 2-inch nail, he should be at about a little bit less than a 3/4 of an inch away from the end of the member, you know, and just keep that in mind. In other words, it has to be at least 1/3 the nail length away from the end of the member where he's driving the nail. That's it. So that's for toenailing. Now, nail clinching. Who can tell me what does it mean when we're clinching a nail?
Isn't it when you like bend the end of the nail when it exceeds?
Exactly. In other words, when the nail exceeds your lumber and you want to bend it over, that's called clinching, okay? Now, there's a right way of clinching and there's a bad way of clinching, okay? I'm going to show you the right way to clinch, okay? Because and I'll show you the slide, okay? So this is clinching. In other words, the nail was able to go through the 2 pieces of lumber here, and what the guy is doing is he's bending it over and he's driving it back in. So what you need to do, guys, when you're clinching a nail, okay, the worst thing I've seen people do is they just take the nail. Okay, I'll try to draw this, okay? I'll try to draw this so you guys can see this, okay? Here's my piece of lumber. Here's my piece of lumber. Okay, so my nail is driven through and it come out here. Okay, so here's the head, of course, the head's there. And the worst thing, okay, and here's my nail, okay. What I've seen people do is simply take their hammer, hit it here, and this is what they do. They just make it go flat like this, okay? And they consider that to be clinched, okay? Well, that's not the real way to clinch a nail. If you want to clinch a nail properly, do you know what the claw of the hammer is? Do you know what the claw of the hammer is? You
Is
guys
it
know
like
that?
the back part of the hammer?
In other words, the part where you use to withdraw the nails, you know the part that looks like a V? You understand?
Yes.
That's the claw. Okay, so you take the claw of your hammer, you put it here, and you twist a nail with the claw of your hammer, and you get this type of deformation. And then once you bent it in, you take it and you drive it into the wood. That's what you're seeing here. So in other words, he twists the nail with the claw of the hammer to give it a downward angle, and then he drives it into the wood, and that's the best way to clinch, guys. Okay? So if ever you clinch your nails, that's the way it should be done. Okay? Now, if you do it the other way, I'm not sure what the effects have, but that's the right way. And that's what they're showing you here, is that you notice that these nails were bent with the hammer itself. In other words, here's my hammer. I'm going to try to draw a hammer. Anyways, you guys know what a hammer looks like. Okay, so in other words, you know that you have claws here. Okay, in other words, it looks like and therefore you take this part of the hammer and you actually twist the nail, give it a downward angle, and then you take the hammer and you just bang and drive it into your wood. Okay, and that's what they're trying to show you here. Okay, so that's the proper way to clinch. Now, clinching is only beneficial for single shear. If you have double shear, it has no benefit, so keep that in mind. Okay, so one for unclinched nails in single shear. Okay, and then if you happen to clinch your nails, wow, this is really good, because a clinched nail, look what happens. It brings it up to 1.6. So you increase the resistance by 60% if you're clinching. Mind you, it takes more time, okay? But this, again, keep in mind that the clinching, 1.6 for nails that are single shear and clinched at the far side, okay? In other words, the clinch portion of the nail should be at least 3 nail diameters long. So in other words, if all of a sudden I have my nail is sticking out of my wood here, and here's my wood, okay? And if this happens to be less than 3 diameters, well, you can't even consider that to be clinched, okay? So in other words, one of the things that the nail, so for example, sometimes you see these guys, the nail head just pops out of the wood like this, and then they bend it over. That's not a clinched nail. For you to consider it, to take this into consideration for your resistance, the nail has to be at least 3 diameters longer exceed in order for that to be considered clinch. And if it's not 3 diameters, you won't even be able to bend it and clinch it properly, first of all, okay? So keep that in mind. So this can be very beneficial when you're in single shear and you want to reduce the number of nails, because look, if you tell the guy to clinch the nails, wow, you're increasing your whole resistance of your nailing by 60% right there, okay? That could really help you to minimize, certain things. So these are, and then the last one, the JD, well, we're not going to get into that, but the JD is for diaphragm construction. In other words, diaphragms are used to resist lateral loads for, like for wind and for earthquakes. And because it's such a temporary load, okay, 1.0 for nails not used for facets and shear walls and diaphragms, okay? And if you're using nails as part of your diaphragm, you're allowed to increase, just because wind and earthquakes is a very temporary load, this is like, is like taking advantage of the fact that you could increase the temporary resistance of that nail. But we're not even going to consider this. We're just going to take JD to be 1.0. So that's the 4 J's. And now here is the figure 7.4, gives the minimum required end distance, edge distance, and nail spacing, okay? And I want you guys to look at this, and I'm going to try to show you, okay, the difference. Okay, first let's start with something simple. Okay, now let's start with something simple. First of all, here's a species. Keep that in mind. And of course, we're going to be using the values on this side because we're using SPF. That's number one. Number two, we're going to be using common nails. So we're going to be using this part of the table here. Okay, we're not going to use spikes and we're not going to use spiral. And of course, depending on the length of the nail, starting from 2.5 inch, okay. And like you see, the table started at 2.5 inch because that was a construction industry standard, using minimum 2.5 inch nails for anything and then work your way up. Now, here is I won't even talk about, let's talk about here, but it's the same thing, A, B, C, D. Here they're trying to relate to you what A, B, C, D is, okay? And if you can relate to these figures, A, B, C, D, you will not make a mistake. Now, what they're trying to show you here is, okay, let's start with A, okay? Minimum spacing parallel to the grain, okay? So for example, my lumber is going this way in this piece. So therefore, this is the, okay? And therefore, A would be the distance parallel where the orientation of the grain. So in this, for this piece here, this would be A, okay? But not, okay? Now, and if my lumber is being placed in this direction, the grain is going this way, and therefore A is always parallel to the grain. So the first thing you have to worry about in which direction is the grain, and therefore that it will help you to determine what the value of A is. Now, what they're saying here is that if I start putting a series of nails to do my joint, you need to have a minimum of 52 millimeters. I never use 52. Okay, I use 60, I use 70, I use 80. This is minimum, guys, okay? So don't ever even consider that. So this is minimum spacing parallel to the grain. Now here you'll see my member is going diagonally here, okay? But the grain is going like this, and therefore you're always going parallel, like the distance parallel to the grain, okay? So in other words, A would be, okay, same thing here. The grain is going this way, and that becomes your A value. So that's what they're trying to show you here. You look at the orientation of the grain and not the member to determine A. That's what you have to keep in mind, okay? Number two, let's look at B. B is the minimum end distance. So in other words, this is where the member ends. This is where the member ends for the one in the back, okay? So therefore that would be B, that would be B. So in other words, you should keep at least that much distance between where the member ends in the back or where the member ends in the front, and that is your end distance, okay? And of course, here is your B value for this member here, okay? And here is your, okay, so that's, okay? So you have to look at, so for example, here, from here to here, that's where the member ends with respect to this line of action here, and therefore that becomes your B. Same thing here. So always keep in mind, you're always looking at the angle of the wood. In other words, you're assuming that the grain is going that way, and that is your B value, okay? So that is your B, end distance. Now, minimum spacing perpendicular to grain. So in other words, what this means is that if I want to put a series of nails, okay, well, this is the distance that is perpendicular to those nails. In other words, this is the and therefore, if I want to see if I can put 2 rows, 3 rows, well, this is going to tell me if I can do that, because I need this minimum distance between those rows in order for me to be able to have 2 rows, 3 rows, and so on. So this is the minimum distance perpendicular to the grain. So for example, okay, so here, for example, here again, the C value is always a distance. Okay, you're looking at the distance perpendicular to the grain. So they're telling you, take the distance from there to there. Take that perpendicular distance there. Don't take that one, you take that perpendicular distance there. So it's as if you extend that line and you try to find what that distance is between there and there. And that would become the perpendicular distance. And of course, the last is the edge distance. In other words, how close can I put the nail to the edges, okay? And therefore, this tells me that the closest I can put this nail is 13 millimeters here, 13 millimeters there. So this is an edge and this is an end. So don't confuse the two. This is an edge and this is an end. So that's why they give you, this is the D and that's the D. So depending on the size of the nail, well, of course, the bigger the nail, the further apart these distances become, okay? And therefore, A is 52 millimeters for a 2.5 inch nail, 59 and so on. And okay, so for your distance parallel to the grain, the end distance, the perpendicular to the grain, the edge distance, well, that's where you come and get the values here. And like I said, the example I'm going to show you, 52 is a minimum, I will be using 60s, I will be using 70s. 39 is a minimum, I will be using 40, you understand? The only time I will look at this is I will see, do I have at least 26? If I have 26, then I can consider putting at least 3 rows. Now, what they're telling you here, last but not least, okay, if you respect all these dimensions that are in the table here, you are allowed to stagger nails in between. In other words, if I maintain a minimum A distance, I maintain a minimum C distance, so on, I'm allowed staggering nails in between. Okay, that's what they're trying to make you say here. So these stagger nails, in other words, in between here, like right at the midpoint of those 4 nails, I can put another nail there, I put another nail there, another. That's only if I can maintain that, and that. I am allowed putting additional nails staggered diagonally between the rows are permitted. So here, if I have at least 52 here, and if I have at least 52 here. Now, why do they have an A in this direction here and an A in that direction there for this joint? Why do I have 2 A's here?
Because it's centered?
No, it's because this A is for this lumber here and this A is for that lumber there. So the lumbers are joined in different directions. Therefore, when you're looking at this lumber here, you have to maintain the A for the one in the back, and then you have to maintain this A for the one in the front. Does everybody see that?
Yeah.
Okay. And that's why you have 2 A's there. Like always worry about the orientation of the grain when you want to determine your A's. So for this piece of lumber here that's in behind it, my grain is going this way, and therefore I have to maintain, right? And here the orientation is going this way, and then I have to maintain, okay, parallel to the grain, parallel to the grain. And that's why they're giving you 2 A's in this side, okay? And that's why they're giving you 2 D's here. In other words, the edge distance here. Okay, we'll come back to this table. We'll come and get the values. And like I said, these are minimum values, okay? And we will, of course, like I said, you worry about the species, you worry about the length of your nails, and then you come and get the minimum A, minimum B, minimum C, minimum D. And if you meet these minimums, you're okay. As long as you're over and above them, you're okay, okay? I mean, I don't know why people try to, just because it says 39, everybody tries to put 39. It doesn't make sense. Put 40. Put 40, put 50, you understand, as an end distance. Put 40, put 50, don't put 39. But for example here, 44, I would put 50. 49, I would put 50. I would put 60. I would put 80 here. I would put 90 there. I would put 100 there. Understand? Use multiples of 10. Understand? The carpenter, believe me, he's not going to take out his millimeter stick and worry about these dimensions. Okay, clear drawing. Okay, before I leave this table, does anybody have any questions? It's all clear? Okay, now, for nail joints made up of 2 different species, the resistance of the joints must be based on the weaker species. I said that before, so in other words, if I'm joining a Douglas fir piece of lumber with a SPF or a Northern, I always take the weaker one to calculate the number of nails in the joint, okay? So you always base yourself on the weaker one. Now, pre-drilled holes are recommended when nails greater than 4.88 millimeters in diameters are used, okay? This will reduce the occurrence of the splitting. The pre-drilled hole should roughly equal to 75% of the nail diameter, okay? So if the guy tells you, like for example, I'm trying to remember, if you're using inch, I think once you go over 4 inches, when we go back to the table, look at this. I think once you go over 4 inches, you're going over 4.88 for the nails, okay? And therefore, it is recommended that if you're using nails that are greater than 4 inches, that you should pre-drill. And that's why nobody ever uses nails that are over 4 inches to fasten lumber together, because they don't want to go through the trouble of having to drill, okay? So there's really no, so keep this in mind, okay, that it is recommended. And of course, if you use the spiral nails, it's going to reduce the chance of splitting. So therefore, you might even go a little bit longer. Now, here are some, I want to give you an overview. Fasteners used for wood construction, okay? I want to give you an overview of what we tend to use to fasten wood construction, okay? Number one, okay, of course, we can use bolts. There's, you know, if you have, for example, you have these stirrups here, okay, that you would make, okay, you would actually make them, okay, and you want to fasten the stirrups to your lumber, and you can bolt everything together. So bolts is one option, okay. So don't be surprised that you know, people will bolt things together, especially when you start looking at heavy timber. So it is very common to have these stirrups, you know, like I call them stirrups, but in a sense, supports here, I call them stirrups, and everything is bolted together. So this is one, okay. Of course, wood screws, I didn't have an example. I guess you guys have all seen wood screws, and I figured I didn't bring any examples of wood screws. And that's another fastener that is very commonly used to fasten wood together. Now, this is a drift pin, okay? This is similar to those spikes that we saw, okay? Whereby you will drill the hole through the lumber, okay? And it's just basically a dowel, okay? They call it a drift pin. And therefore, you will drive the dowel through the lumber and fasten it, you understand? Drift pins on opposite diagonals in a layer. So for example, this hole goes through this one, and then when they put the next piece on top, well, then they'll put a drift pin in that one and that one, and then when they put the other piece, they'll put, in a sense, so that's how they're gonna assemble everything together. So these two will help to assemble these two together, then they put another piece. So these are called drift pins. If you ever hear the word drift pins, this is what you're looking at. Now, this is a very common fastener that you use when you want to get a lot of resistance from a screw. So instead of using wood screws, this is a very common, okay, fastener. This is called a lag screw. The handbook has all the values for all different sizes of lag screws, and this diagram shows you all the values that you have in the tables and explains. So this is called a lag screw. In other words, this has a hexagonal head here, okay? So for example, whenever you have these big side plates that are made out of, you know, plates like steel plates, and you're using that to make your joint, and you want to be able to fasten the steel plates to the lumber or to the timber, one of the most common things that you use are lag screws. So it looks like a screw, but it's got a, you know, like they're very, very good. If you hear the term lag screw, like I said, and in the handbook, you got all the values that you can need to be able to determine how many of these you need to be able to do your joint. Now, I've seen this, okay, these are called timber rivets, okay? So in other words, they actually look like this, okay? And they're very, very common, okay, used to fasten the joist, or in this case, the hanger. I'm not gonna call this a joist hanger, but this is like a beam hanger. Okay, very, very common to fasten.
That's what I was talking about earlier.
Oh, the timber, the rivets then. Is that what you're talking about? Okay.
Yeah.
Okay, I understand. And you thought these were spikes. Is that what it is?
Yeah, exactly.
Now you know that they're called rivets, okay? Omar?
Are those plates with them already like welded onto it, or do they go through the plate?
Well, no, these plates have holes in them.
Okay.
Okay, like these are all pre-drilled holes. And then what happens is that when they get to the job site, once they put this big girder here, then the guy goes and he places this here, and he fastens it with the rivets, and then they'll come in and put this beam to be sitting on. And you know, when you're calculating your LB and all that, well, that's what this is right here, your LB required. You see?
Because I think I'm thinking the same thing that Omar is thinking of, where it's like a plate, but it's already welded onto it, and they're
Pre-welded onto it.
And then you just hammer the plate onto the wood.
Oh, those are truss plates.
Oh, okay, that's what it's called.
They're truss plates. Oh my God. Okay, so truss plates. That's what you're talking about.
I guess so. Yeah, maybe. Yeah.
What you're talking about, okay. So now this here are called shear plates, okay? Now, what you see here, this is the tool that makes the groove, okay? So don't look at this, okay? This is the tool that makes the groove, and these are the shear plates, okay? And basically they make the groove, and they go in, and then after that, they're able to, like, for example, you see this is where the joint is here, and this is a very nice detail, you know, like when, in other words, when you're looking at something that you're gonna have architecturally exposed timber and all that, this is a very nice detail, okay? So these are used in very, very specific, you know, situations where you want to have a fancy detailing for your joints. So this is called shear plates. This is the shear plate itself, okay? And this is embedded now in the piece of wood, okay? And basically what happens is that this allows this whole area here to bear against the wood as opposed to just a single diameter nail. So therefore you get a lot more surface area, and that's what these things do. So these are called shear plates, okay? So this is what bears on the wood, and of course you put the steel plates across them, and of course you put your bolts. These are bolts, and you just bolt them together, okay? So this is a nice detail. So you can either go with shear plates, and then another fastener are called shear rings. This is a little cheaper, not a, you understand? A little cheaper, but same thing. This is the tool that actually will make the groove in the wood and make the hole, and then you put your shear ring here, and then this gets sheared. This gets shared between that piece of lumber and that piece of lumber. Understand? And then the same. You would have the same thing on the other side. You'd have another split ring on this side to connect that with that, and then you bolt everything together. So these called are split rings, and these ones are called shear plates. Okay. So this is a nice, also very nice detail when it comes to. So if you're going to be using side plates made out of lumber here, as opposed to using metal, then I would use shear plate, split rings, because this is made for that type of. And if I'd be using side plates made out of metal side plates, then I would be using shear plates. So that's where I would decide which one of the two. And of course, the people that sell these things, they will also sell you this tool, because this tool is going to give you exactly the diameter and everything, and the groove that needs to be made in the wood for this thing to sit properly, halfway in and halfway out. So therefore, this gets shared equally between this piece of wood and that piece of wood. Okay. So in other words, whatever length you have here. Oops, sorry. So whatever length you have, where's my, so whatever height this ring is, you can appreciate that half goes, so the groove here would be half that ring that would go on that side, and the other half would be on the other side. The same thing here, half goes into this member and half would go into that member. Okay, it would be split, you know, between the two of them equally. And that's a split ring. And another type of fastener is, of course, this is what you guys are talking about. Truss plates. Is that
Yeah,
it?
that's exactly it.
Okay. Yeah, these things actually, okay, they're just sheet metals, and they get stamped into the wood. Okay, so these are truss plates, and believe it or not, guys, these things have patents on them. Okay, so I mean, all truss manufacturers use these truss plates to make the joints. Okay, you understand? And like I said, there's patents on these truss plates, and the guy that developed the patent, could you imagine, even if he makes 0.001 cent off each truss joint that gets produced in every truss, how much money do you think he's making at the end of the year? Isn't that amazing? So therefore, these are the truss plates, and then of course, like depending on the you know, like the amount of resistance. Okay, like here is very small, so the truss plate would be very small. Here the resistance has to be much bigger, so the truss plate is much bigger. So it's all in proportion to the forces, and of course here. Okay, so therefore these are truss plates. Okay, and you can see here that the lumber has a certain length, so they had to make a joint there, and they had to make a joint there, and then they had to make a joint there. Okay, so it's very common to have, like in your bottom cord, because you can appreciate, look at the span of this truss here. There's no way that you'd find lumber that's got like a 35-foot span. Okay, so they probably used 12 feet, 12 feet, and 12 feet, and they made the joints there. And then the same thing here. They couldn't find a piece of lumber here, so they made a joint there, and they made a joint there. Okay. And of course, these joints are analyzed as if it's pin connected. You understand? They don't transfer the moments because they're not stiff enough. Okay. So all these things would be, like here it would be continuous, and this would be pin connected to that. That would be connected, but this would be a continuous member. So that's what you have to keep in mind. So, and then of course, like I made yours simple. I made yours right in the middle just to simplify the modeling. But in reality, nobody puts a joint right in the middle, because as they lift the truss, that's the worst place to have the joint. It's most likely going to break there. And well, here you go. This is lifting the truss and putting them in place. You understand? This guy has a nice job. All he's doing is that as they place it, he makes sure he nails it so it stays in its place. And then after that, of course, they have to brace all this together and so on. So these are what you're talking about. So these are sheet metal, right? In other words, just galvanized pieces of steel, 14 gauge, 16 gauge, 18 gauge, I don't know. I really don't know what the thickness of the sheet metal is. And of course, they get stamped right into the wood, okay? Bang. And it's kind of like, and of course, you're relying on all these penetrations into the wood to give you the resistance, okay? That's what's happening, okay? So these are truss plates. So these are not rivets, they're truss plates. So now you know the right terminology. And what else do we have? Oh yeah, of course we have our joist hangers, right? And keep in mind that there are two types of joist hangers. Face mounted, in other words, here's the beam, face mounted, and of course top mounted. In other words, it gets nailed on top of the beam. Now, some people don't want to have this because when you put the plywood, this might cause a little unevenness in the flooring. So therefore but if you don't have a problem, if you have no sheeting on top of the, if you have no subfloor on top of your beam, you might want to consider top mounted as opposed to face mounted, okay? And of course, the LB required, well, there's your LB required. So when you do your LB required, you got to make sure your joist hanger has that space there. LB provided greater than your LB required. And that's what we calculate that for, okay? And of course, at the end of the day, you'll be able to calculate how many nails you would need here, depending on the size of the nails, and depending on the size of, because then here you would take, for this nail here, you would take, your side plate is sheet metal. You would ask the guy, what's the gauge thickness of your sheet metal? He would say, well, it's 14 gauge. Well, you go into the table 14 gauge, and then you'd be able to calculate how many nails you need to support. You know, you have a shear force here, your VF, and therefore you calculate how many nails you would need to hang your, and that's why here you have much more, because here the nail is acting this way, and of course you got all of this to help, okay? So therefore the nail is acting totally different here to resist the shear force as opposed to these ones here. So you can appreciate that it takes more nails when it's side mounted versus when it's top mounted. So that's the difference. And I think that, oh yeah, one more thing I want to show you. So you guys, okay. And then of course here, okay. So when you have big, for example, here, if you don't want to use joist hangers, you can use these brackets, okay. These are brackets. And of course, this here is very important when you have a lot of uplift, okay? You want to be able to, so in other words, if your toenailing is not sufficient to hold the rafters of your roof up, you might consider using these brackets to tie down. And then of course, you should even tie down the studs that are going to be subjected to the uplift, okay? So this is all has to be calculated to make sure that, you know, when the wind blows over your structure, your roof doesn't blow off. And then on top of that, it doesn't blow off the wall. So this has to be, now keep in mind, okay, keep in mind. So if you are going to be putting a sheet of plywood here, okay, if you're going to be putting a sheet of plywood here, okay, and if you're going to calculate the number of nails that you put in the sheet of plywood is going to be nailed to the bottom plate, and they're going to be nailed here. So this might replace that, okay? But if you don't have nothing like that to transfer this to there, you might consider using that bracket, okay? And of course, there's different types of brackets, okay? And of course, at the roof, this is very, very common, okay? This is very common to tie down the roof properly. These brackets are very, very common, and that's what they're showing you here, okay? And of course, this is, instead of using joist hangers, you can use brackets if you want, right? So this is another type of fastener that you can use, yes?
Are those called hurricane clips?
These are called hurricane clips, yeah.
Okay, and even for the stud, right? To the right of it?
Even for the stud, yeah. They're yeah, like they're called hurricane clips, and that's because they're done for uplift. They're installed for uplift. That's why they call them hurricane, because the hurricanes have a great uplift force. Okay, so that's the hurricane. If you guys want to see a variety of how many fasteners there are out there, and there's a company called Strong Tie. They have a beautiful catalog. You should find them on their website, Strong Tie. Okay, and beautiful catalog. I mean, I've got their catalog because sometimes I need to find a specific type of fastener. It's a beautiful, and you can just download their catalog, and you should see the vast number of, and that's all they do. They just make different types of fasteners for wood, for concrete. Oh, it's amazing. So the company name is Strong Tie. Very good company and very beautiful catalogs. You just go to their website, and you can download their catalogs, and you'll see. And they, of course, they have tables. They'll give you all the information on how to calculate what you need. All you need to determine is what force you want to resist, and then you just go into tables and see what you need. So very, very convenient for that. As a matter of fact, they came up like right now, because I don't practice anymore, so they came up with this new thing, a new fastener, which was really neat, and I thought it was really neat. And it doesn't come to me right now, but so if you guys are interested, Strong Tie is the name of the company. And they're really nice catalogs when it comes to fasteners. And you'll see all of these. They're like, you'll have so many of them in there. Now, let's take everything that we learned and let's apply it to make a joint. Okay, so this way we can start, being practical. So here we go. So here is, a typical situation where determine the size and number of nails required for the plywood. Tension splice shown below. Of course, it's in tension because this member is being pulled, and the lumber members are kiln drying. I'm giving you this because use 38 by 140. In other words, this would be like this is a 2x6 SPF, and the plywood is a 12 millimeter sheeting Douglas fir. I threw in Douglas fir here so that we can, because on the project, we're going to be using Canadian softwood plywood. So therefore, I want you to be able to use both tables. Now, the factored force here, TF, is 8 kilonewtons, okay, due to snow and rain. So in other words, the guy, what he did was very simple. Very simple. What he did is he had his truss, okay? He's got a joint here in his bottom cord. Okay, he's got a joint here in his bottom cord. And from his analysis, he found out that bottom cord had a force of 8 kilonewtons. And now he has to be able to splice the two pieces together so that the joint can transfer the load properly from one side to the other. Okay, and that's what that is. So now, first thing you're going to do is, of course, determine the modification factors. KD is 1, perfect. KS is 1, perfect, because we're talking about a truss that's going to be, okay, we're using dry service conditions, okay? In other words, we're going to use dry lumber, we're going to be in dry service conditions, and we're going to be treating untreated wood. So therefore, 1, 1, 1, of course, that means our K prime is 1, okay? So this is something, I'm doing this, more to remind you guys that you should always keep in mind how these factors can affect the resistance of your calculations, okay? And when it's not 1, 1, 1, they're always less than 1, except for a short term, which is the only one that goes higher than 1. And if you forget that one, it won't hurt you because you're just neglecting of taking benefit of that situation. But all the other ones are less than 1. And if you forget 1, that can hurt you. So keep that in mind. Now, J, 1, because it's nailed in the side grain. 1, because we're not toe nailing. I hope you guys can see that. Do you want me to go back? Okay. In other words, the nail here, the nail is being driven like this, and therefore we're going into the side grain. And of course, the grain of this material here, that's the grain of the lumber, because the lumber is always produced with the grain parallel to the length. And therefore, as far as this lumber go, we are driving it into the side grain. We're not driving it into the end grain here, okay? So that's what we're doing there. And now, clinching. Why don't we apply clinching? Because we might have double shear, okay? So therefore, we don't worry about clinching. And of course, we're not in a shear wall or diaphragm. Therefore, we'll take JD to be number 1. Therefore, our JF is also 1, okay? So remember, like if you're going to have a single shear plane and you're going to clinch, well, that's going to be very beneficial. This can bring this up to 1.6, and it can, seriously reduce the number of nails that you're going to need. Now, So that's for K and for J. Now, try 2.5 common nails driven from alternative sides of the main member. What I'm trying to say here is that if you look, okay, here's my main member, okay, and what I want to do is, of course, okay, there's my side plate, there's my side plate, and so on. And of course, the joint would be, where is that stupid? The joint would be somewhere in here, okay? Now, what we want to do is when we're driving our nails, okay, what we want to do is we want to drive one nail with the head on this side, and then one nail with the head on this side, okay? Now, keep in mind, the reason why I say 2.5 inch nails, because this is 1.5 inches. This is 1.5 inches. This is 1/2 inch. This is 1/2 inch. So therefore the nail should end up flush with the end here, okay? And that's why I'm saying use 2.5 inch nails, which is a common thing to do to be able to drive this into the other side. So now we go to the nail selection table. So we said we had SPF lumber and we had Douglas fir side plates. And I said, did we say that the side plates were 1/2 inch? I don't even remember. Did we say that the side plates was Douglas fir and the lumber was SPF? So if we go to the table, we look at two values, okay? We go to the table, and of course, so we don't have lumber side plates. We have Douglas fir side plates right here, okay? So and we're using 1/2 inch thickness plywood, and we're using 2.5 inch nails. Now here where you see the diameter of so remember what they said, when you go over 4.448, they recommend that you pre-drill the hole. So for a 5 inch and a 6 inch nail, you should pre-drill a hole if you're going to be using that to fasten your lumber. So here, now for now this is the side plate, but this is the lumber, and therefore the minimum penetration is 16 millimeters. And therefore, if I have 16 millimeter penetration, I have the NR prime NS value equal to 0.412 kilonewtons. That means for every nail that I will be placing there, I will get that much resistance or factored resistance from that one nail. So that's for the minimum penetration. And then here for the same thing, 1/2 inch thick Douglas fir plywood, 2.5 inch nail. And for SPF, the maximum penetration is 30 millimeters. So even if I go over 30 millimeters, the maximum value is 0.560. Okay, so that's the two values I get from this table. Okay, so that's where I get from that. And now, so I get, okay, and maximum penetration, okay, has to be greater than 30. In other words, if I have 32, 35, 38 millimeters, I can rely on an NR prime NS value of 5.4 kilonewtons per nail. Now, I need to determine, do I have one shear plane or do I have two shear planes? Now, okay, so basically the actual penetration is 38 millimeters. So what this means is that if I look at my lumber that I'm joining here, it's a 2x6, and therefore this lumber here is going to have, this lumber here is going to be 38 millimeters thick, and therefore when I have my side plate here and my side plate there, when I drive my nail through it, it's going to penetrate 38 millimeters, and therefore I have my minimum 30. So therefore I can rely on this value to calculate the resistance there. Now the only thing I need to determine is, do I have one shear plane or do I have two shear planes? Because if I have two shear planes, it's going to take half the number of nails. If I only have one shear plane, it's going to take me twice the amount of nails. So that's number one. So now, so NS number of shear planes. We saw from the table that a 2.5 inch nail has a diameter of 3.25 millimeters. That you get straight from the table. Okay. Now, if you remember, 3 nail diameters for the wood member, that is nailed head for the shear plane. So here on this side, when I put the nail head on this side, this is the nail head here, the thickness here, of the wood has to be 3 times the diameter of the nail. So in other words, 3 times 3.25, which, okay. So that's what it has to be on that side. So I go, I do the calculation, and 5 nail diameters for the member with the point for double shear. In other words, the point will be coming out on this side. So I do the calculation, 3 times 0.25, 9.25. It's less than 12.5. In other words, my side plate here is 12.5. I'm okay. So I can consider that to be a shear plane right there. That's okay. Now, when I look at this shear plane here, when I look at the shear plane here, sorry. So for this shear plane here, not a problem. I meet all the requirements for that one when the nail is driven on that side. Now, when I come to this side here, can I consider that to be a shear plane? Visually, you say yes, it has to be a shear plane because my nail is going to come right up to here, to the point here. But if you do this requirement, 5 times 3.25, you need a plywood thickness, or you need a wood thickness of 16.5. You only have 12.5 for your side plates, so you don't have a shear plane. Even though visually it looks like you have a shear plane, but because your side plate is not thick enough, you cannot consider to have 2 shear planes. And that's the mistake that a lot of people make. Like I said, in our days, when we would calculate this, we would calculate this as 2 shear planes if you'd use a 2.5-inch nail based on what we used to have in the old days, and now that's no longer good. That means all my joints and my trusses have half the nails that are required. So, and I have to sleep with that at night, okay? So now, so in this case here, because I do not meet the requirement on the pointed side, I have NS is equal to 1, not 2. Now, so here we go. So now I've got all my values, right? I have all my values, and therefore I can just calculate the NF, the number of nails required. So therefore I put the values. This I've established that because I have 38 millimeters of penetration, I need a minimum of 30 to use this value here. I'm okay. And I have a value of 1 for the number of shear planes. The NF is the number of nails, and I've determined this to be 1. I need 14.7 nails. So of course you will not put 14 nail. You would put at least 15 in order to satisfy your design requirements. Use 50 nails per side of joint. So that means that, I mean, this is, okay, so in other words, there's a joint. I need 50 nails on this side. I need 50 nails on this side. I don't need like 7 there, 7 there. That is wrong because that force has to get transferred to that number of nails through the lumber and to that number of nails back into the lumber. So I need 50 nails on this side. I need 50 nails on that side. I've seen people say, oh, I need 50 nails. I'll put 7 here and I'll put 8 there. That's wrong. Okay, so you need 15 on each member in order to transfer that force properly from one member to the other, and hopefully that your ply won't split here. Okay. Now, so now determine the maximum spacing, the minimum spacing and edge distance. Okay, so we go back to this figure here. Okay, we go back to this figure here. We know that we have, now this is where people make a mistake, okay? They say, oh, I've got Douglas fir side plates and therefore I can use the values here. No, your side plates got nothing to do, it's a lumber that you're fastening. You're actually fastening SPF, not the Douglas fir.
Sir,
Okay.
can you zoom in? The like.
Oh, zoom in on the table? Sure, hold on a second, hold on. Let me just, is that better?
Yeah.
It's just because I wanted you to be able to relate to these diagrams before, you understand? So here you go. Anyway, you're going to get a copy of this table when I finish the lecture. You're going to get everything okay? So here, so this is, so in other words, SPF is what I'm using. This is the lumber that I'm fastening, and don't make the mistake of using Douglas fir, okay? So this is my A value, the distance parallel to the grain, B value, the end distance, C value, the distance perpendicular to the grain, D value, okay, edge distance. So that's where I come and get these numbers here. And I go back, so that's where I get my A, my B, my C, and my D. Now, you'll notice that here what we've done is, like they said that you need a minimum edge distance of 26. We provided 35. Isn't that nice? We provided 35. Here you need a minimum end distance of 40. They provided 60. This is straight out of the textbook, guys, okay? And then here, this looked like it's 30/30, but this is the A value there. Okay, this is 60. The A value is 52. They provide 60. So you see, everything is done in multiples of 5, multiples of 10. Okay, and then eventually, even here's the end distance for this is the end distance for the lumber. This is the end distance for the side plate. This is the end. So in other words, and of course, whatever you do this way, you would just on the drawing you would put, okay, center line, and you would put S, Y, M, M, and what would that mean? That it would be symmetric, and the guy would do exactly the mirror image of that on that side of your joint. Okay, and that would determine what is the length of your gusset plate. Okay. So that's, like I said, we're going to be doing one in class, okay? I mean, we're going to be doing one in the lab for our truss, and then after that, you guys are going to be doing all the joints to finish, and that's going to be the end of the design for the project, guys. There won't be anything else after that. How are we doing time-wise? Oh, we got time. Okay, so let me clear this. And that's it. So guys, do the assignment. Okay, I do strongly recommend you do the assignment. The assignment is going to be, I think, is going to be lumber to lumber. I want to change it up a bit. Okay, and I think, anyways, do the assignment, because I think on the exam I'm going to give you. I'm not sure if I'm going to give you a problem similar to the assignment or I'm going to give you a splice. I'm not sure what I'm going to do, but do the assignment and make sure you know how to do both. And that's it. So the assignment should be coming out by around 5 o'clock today, and just have it done by next Thursday. So that's it for that. Now, what we can do, let me close this. Like I said, I'll be sending you this. Now, let's look at our project and let's look at our trusses, okay? Now, we have about, we go till 5:30, so we got time, guys, okay? Got time. So let's go here. We'll talk about the project now from the beginning, okay? Truss joints, okay? Now, and trust me, when I was your age, this is not the type of joints that I used to worry about, you know. So axial forces. So this is what you got from ADA, okay? And guys, it looks very ugly here, okay? But basically what this does is it tells you all the axial forces that are in your member, okay? Now, keep in mind, I'm gonna do this, okay? Keep in mind, okay? This member here is continuous. So am I going to have to worry about doing any nailing in this member? No. This member here is going to be continuous because you can find lumber that's going to be that length. So as far as you're concerned, there's going to be absolutely no worries about, and then here, the members in compression, they're pushing together. So do I even worry about the nails there? No. Okay. Now, what you need to worry about is the joint for the web members, the joint for the tension members. In other words, you have to worry about this tension force here that you have to join this to there. You have to worry about the tension force of the splice. You have to worry about the force here in this member here in case you have a reverse, okay? And then you have to worry about the force in this member here. Now, let me just, so here is, okay, now, the number of nails, so this is basically your joints. The number of nails that I calculate for joint number 1, I'm going to be putting the same number, I'm sorry, for joint number 2, I'll be putting on joint number 1. The number of nails I put here is what I'm going to be putting here. So here I have absolutely no joints. The number of nails I need to join this member to that member, I'll put the same number of nails here, the same number of nails there. And then here, of course, for joint number 5, it's going to be the sum of the nails I need here and the nails I need here. So here I'm going to have the sum of these two joints. So here the joints are going to look like, it's going to be, okay. And therefore, okay. And what we're going to do in the lab is we're going to do this joint here, and then I'll expect you to do all the other joints, okay? So these are the joints. So in other words, you have to design this joint. You have to design the spacing for this joint here, because here your gusset plate is going to look like this. Okay, so here, you know, you're gonna have to make sure you have the right spacing here and so on and so on. So the objective, what I'm gonna be looking for is the number of nails. Once we calculate the number of nails for this joint here, you're gonna use the same NR value for everything else. So that's gonna be a piece of cake. Once I've established the NR value for one joint, it's the same NR value. So for example, here, if I have 7 kilonewtons, I divide that by that NR value, that gives me the number of nails. All I have left after that is determine the spacing. So that's going to be
sir,
yes.
it's not necessarily that it's a what's it called? It's like an image. If you do the left side, it's the same as the right side, right?
Oh yeah. I always once I calculate this joint, that becomes the same thing.
Okay.
Exactly. In other words, you're not going to be doing this joint and that, because they're exactly the same forces. If you look at your ADA, the force that's in this member here is exactly the same as the force in that member there, and the member here is the same as that. This is pretty messy, and that's why I don't like to look at it this way. But I mean, this is the tension force in this member here, and this is the tension force in this member here. This is the compression force in this member here of whatever it is, 5.06, and I have exactly the same value here. You understand? It's very messy when you're looking at axial forces in ADA. I mean, I personally, I don't bother. What I do is I simply, I do myself a sketch like this, and then I click on the member and I write the force here. Understand? And I write the force here, and I write the forces on my diagram. So this way I don't take the wrong one. See here, I don't worry about this 21 here because I don't have to join anything here. So I don't even worry about the 21. I don't worry about any of the force in this member here because this member doesn't have to be joined. It only has to be joined up here. And it's only when I join this member to that member and that member to that member, that's all going to get joined together. Okay, so you're right, Omar. This joint here will be exactly the same here. So, but on your drawing, you're going to point this as joint number 3, and then you're going to have a schedule. You're going to put joint number, right? And you're going to put the number of nails that you need to have for joint number 3. That's what you're going to show on the drawing. That's why you have to point them. So the carpenter knows how many nails to put there, how many nails to put there, how many nails to put there, how many more, and so on. Okay, that's why it's just.
Sir, I have a question.
Yes.
Oh, what if, because my right side and my left side, some of them are not the same. Do you want me to recalculate them both, or I just use the higher one?
If they're not the same, something
It's like
bizarre.
then something's wrong. Okay.
No, it's bizarre. I mean, like when you're telling me that it's not the same, like how much of a difference are we talking about?
Not much. Maybe 1 or 2 kilonewtons difference.
Oh, kilonewtons. It's not like we're not talking about like 0.1 kilonewtons. We're talking about 1 or 2 kilonewtons.
Yeah, I think so.
Okay, I suggest you look at your modeling and make sure you've released everything properly. That's what might be giving you the different values. Okay.
Okay. Thank you.
And guys, I want you to do this once in your life so that you can appreciate. Okay, that. If ever you do, for example, you analyze a truss on ADA, okay? You analyze ADA, everything is fixed, okay? And then what you do is you know that a truss has to be analyzed, a steel truss has to be analyzed as a pin structure. So therefore you pick all the members and then you go to MX, okay? And you go down, you put a 0, 0. ADA is going to release all the connections and make them pin connection. And if you zoom in, you'll see that for example, here, ADA will have a circle there, will have a circle there, but and it will not put a circle there. Remember I told you, you never pin everything. You only need to pin 3 of the 4 members or 2 of the 3 members. And I've always seen people pin here. And that is like, even ADA does it by default. I don't know where you guys get this thing about pinning on both sides when it's a pin connector, you know. So I just wanted to let you know that if you want to try it on your own. Okay, so here we go. So this is it. So these are the joint numbers, okay? And of course, what I did for you, if you want to copy these down so you can have this or take a screenshot, here's the force in joint number 1. Because it's the same force as joint number 2. Because what you're actually doing, okay, is that this is the top chord here, this is the bottom chord here. So therefore, here you have a force of whatever. Sorry, I can't see that. 17. So you have a tension force here of 17.88 kilonewtons, and therefore, this has to be able to resist when you put your gusset plate here. This has to be able to. So now the number of nails you have here will be the same number of nails you have there. Okay. So that's joint number 1, joint number 2. Then joint number 3, this is the force for joint number 3. This is the joint for joint number 4. Here's a joint number 5 and joint number 6. So you've got all the forces, okay? This is the actual force that the member has, and that's what you actually design the joint for. And of course, I think we're going to be doing joint number 6. In other words, the splice in the middle, just like we did in class, right? Now, so this is what you have, okay? Now, if I'm not mistaken, we said that we decided that a 2x4 was good enough for the bottom chord. Am I correct?
Yeah.
I'm correct. Good, thank you. And we said the top chord is going to be a 2x6 and the web members are going to be 2x4. So keep that in mind, okay? Now, this is the force that the member has to resist. So in other words, I have to calculate the number of nails I need to put on this side. And of course, I'll repeat that same number on that side. And then I need to calculate the length of this here. And then this is going to be the length of the splice plate. Now, I just have to show this on the drawing. I don't show this dimension. Why? Because the carpenter is smart enough to realize that this is going to be the size. This is going to be the size of the 2x4. Okay. Anyways, look at the typical drawings. You'll see what dimensions you have to put on when you're actually dimensioning the gusset plates. I gave you those sample drawings. Now, we will do the same thing that we did in class. Okay, we will have KD is 1, KS is 1, KT is 1. Perfect. And the same thing as the example. So therefore, K prime is 1, and the same thing. We're nailing into the side grain of the lumber that we're making the truss with. We're not toe nailing, we're not clinching, and we don't have any shear walls or diaphragm, and therefore our JF is 1. So therefore 1 and 1. Okay. Now I got good practice to do this, because if you can take advantage of clinching, it helps. And some people overlook that. And okay. Now using 2.5 common nails. Why? Because I'm using 1/2 inch plywood, 1.5 inch lumber, 1/2 inch plywood. I want to be able to drive the nails from one side to the other without any of them sticking out. That's number 1. Okay. And of course, we go here now. Now the difference is that instead of using the, okay, so here we don't have lumber as side plates. We're not going to use Douglas fir plywood. We're going to be using Canadian softwood plywood. That's what we're going to be using. It's going to be 1/2 inch thick. We're using 2.5 inch nails. Therefore, we need to have a minimum penetration of 16 into our member. That's not a problem. And that would be the value of N, R prime, and S. And then we need to have a maximum penetration. I'm sorry, I'm looking at the wrong one. This is the lumber. I apologize for that. Let me erase that. Okay, so here we go. I apologize. So here is the minimum penetration, and therefore there's the diameter of our nails. Keep that in mind, and that's the length of our nails. And then of course, for the same thickness of plywood, for the same length of nails, we need a maximum penetration of 29, which I know we won't have a problem because we're penetrating at least 38 millimeters, and that's the value of NR prime NS. So that's what I get from the table. This is to make sure I meet at least this, to have at least one shear plane. And then this is to make sure that I can see what value. And of course, if the penetration was somewhere between 16 and 29, I could interpolate the value if I wanted to, but I won't have to in this case. So let me just minimize that. So for 16, that's the value. For this was 29. I don't know why I put 30. I apologize. I probably copied. So this was supposed to be 29. This is the value. I think I got the right. Did I take the right value here? Did I take the right value from the table? Do you guys know?
I don't remember.
I don't remember.
No.
No. So I took the wrong value.
0.516.
Yeah, so I took the wrong value. So I have to change it. So it's 0.156, right, for 29 millimeters. And it's 0.38. I know what I probably did. 0.38. So I probably cut and pasted the example I did in class, and I didn't bother correcting it. So this is wrong. I want you to correct this, and I want you to correct it. Give me so what's the value we had here? Okay.
0.38.
Yeah,
0.38. Yeah, okay, and then here we had
0.516.
506. So I apologize for that. Like I said,
No, sorry, 516.
516. As long as we have the value, because we're going to be using this value is going to be the same value we're going to be using for all the joints. So we better make sure these are correct. So I apologize for this. This is wrong. This is correct. Okay, so keep this in mind. So I probably use the wrong value in my calculations. It's going to have more nails. That's all. You understand? The actual penetration is 38 millimeters, and therefore I can use. You guys want me to correct this right now, or can we just go ahead and correct it as we go along? So I'm going to just write it down here. 0.51. Pardon?
Is it 5 516 or is it 502? Because I was looking at the table.
Okay, let me go back. Let's go back. That's what I mean. Let's go back and let's be careful about this. And that's why, like, I was a little careless.
Point is
Okay.
Yes, sir.
Yeah, let's go back and take a look. So here we are. First of all, we're right here. We agree.
Yeah.
So that's number one. And we are right here. Right? So it's
Yeah.
0.502.
oh 2. Okay.
Okay, so that's okay. So 0.502 is the right answer.
And for the second one, right?
And here we have a value of 0. So 0.363 and 0.502. Okay.
Sir.
Yes.
So basically, what we did in the class example, it's kind of wrong because you took the left column instead of taking the right column. Because we were under SPF, and you went to the left instead of going to the right.
So I took the wrong value in the class.
Yeah, in class example.
It's possible.
No, he used Douglas for plywood. No.
Yeah, but in class, I think I used. Hold on a second. First of all, I used Douglas fir plywood, so I'm not sure if I used. Did I use 2.5-inch nails? Well, guys, if I use the wrong number in the class, did I use 0.51 for the example? I don't remember. Anyways, I'll correct it. I'm going to correct it before I send you the lecture just to make sure. How's that?
Okay, perfect.
So I apologize about that. I apologize that I took the wrong value. See, it happens to the best of us. So I'm glad we're all so this here, like I said, this is wrong, that's wrong. But now determine the number of shear planes. This doesn't change anything. The 3 nail diameters, this is exactly like the class, okay? 5 nail diameters for double shear. And of course, if we do the calculations, we know that this is okay, but this is not okay. So therefore our NS value is only 1, it's not 2. And what this means is that, unfortunately, when the nail penetrates here at the end here, this has to be at least 16.3 millimeters thick, and we only have 12.5. And because it's not thick enough, we can't take advantage of that shear plane. We only have the shear plane here, because here we need 9.8 and we have 12.5. So therefore, we have a shear plane there. We have a minimum penetration, maximum penetration. That's okay because we have 38 here. So we can go and use the maximum value right away. And of course, that value is 0.502. And I apologize about that. Okay. And that means that our NS value is only 1. Okay. So here we go. Now NS value is 1. So now I can go ahead and calculate the number of nails required. Now guys, can you do me a favor? Who's got a calculator? Change this value here, please. And let's get the right value because we're going to use this for all the joints. So this is 0.502. And therefore this is 0.502. Okay. And I want you guys to read. So therefore, so guys, the NR value for all the joints will be 0.502 kilonewtons per nail. Everybody understands that?
Yeah.
Okay, that means that when I have a force of, let's say, 20 kilonewtons, I simply divide that by this value, that gives me the number of nails. So that's all you need to do for each joint. You have the force and therefore you can calculate the number of nails. What's going to be a little bit more tedious is to calculate the spacing and to calculate the size of your gusset plates. Okay, so here we go. So now, so this is wrong again. Like I said, keep in mind that this is wrong. This is okay. 0.502 will be the same value for all the other joints of the truss. Okay, so that's what we're going to be using for all 0.502, and that's the wrong value. So now we know that we have NR has to be greater than TF. What was our TF value that we had? Was that did I make a mistake here also, or shall we go back and check that?
Yeah.
I did. What was the TF value we had? 11.06. That's what we had.
Looking at the joint too.
Okay, so that's 1106. So in other words, that was our TF value. So at least I did that correct. Now, the thing is, guys, remember, change this to 0.502 502. And would somebody please recalculate this for me?
It's 22.
22 nails.
22 nails. Thank you. Okay, so this is,
Yes.
it's exactly 22, or is it 21 point something?
Well, it's 22.1.
22.1. So therefore you should be using 23 nails, guys. Okay. Okay, keep that in mind. Okay, 22.1, you always want to make sure the resistance is more than what you need to resist the force. So 22.1, as far as I'm concerned, put 23. And like I told you. Okay, so we're going to use 23 nails. Okay, now I'm going to show you how I tend to be able to. Okay, so we now this is the values I got from figure 7.4. We've seen these before, right? Now, this is what I'm going to show you, okay? Determine the number of rows. In other words, how many rows of nails can I put? Can I put only 2 or can I put 3, okay? So basically what I do is a 2x4 is 89 millimeters wide, right? Now, if I look at a 2x4, if I look at a 2x4 here like this, okay? I know I have here 89 millimeters wide. I know according to the minimum distance of the edge is 13. So I need to have at least 13 millimeters here. And I need to have at least 13 millimeters there. So that I need to have at least that, okay? And then as far as the distance is, okay, perpendicular to the grain, okay, I need to have at least 26. So in other words, if I decide to put a nail in here, the distance between here and here, perpendicular to the grain, has to be at least 26. So this is what I do. Just, you know, so what I do is I say 2 times C times 2 times D gives me 67, right? And I have 89, therefore I know I can put 3 rows there. Okay, so that means I can go ahead and put 3 rows of nails, and I will be able to maintain that minimum distance between the edge and in between the 2 nails. So I can put 3 rows of nails in my connection. That's number 1. Number 2, and that's gonna be the same calculation for all your joints, because you're using 2x4 all over. Therefore, you know that you can put at least 3 rows of nails for all your joints. Now, so this is what I do. Once I have established the number of rows, in other words, okay, so this is the nail on the near side. This is how you represent the nail on the far side. In other words, this would be nailed from the other side. The head would be on the other side and the point would be on this side. So this is how I represent nail on the near side. In other words, the one that you're seeing you, and this is the nail on the far side. That's just graphically, so the carpenter knows he'll alternate on which side he puts the nails, number 1. Now, here is my joint right here. Okay, so in other words, whatever I do on this side is going to be symmetric. Okay, so here what I say, I need 13, I will put 15 millimeters edge distance to give me 2 millimeters of, you know, and I'll put 15 here. And then I'll tell the carpenter, put it right down the middle. I don't even care because I did this calculation and I know that I need at least 26 and I got more than 26. Because if I do, in other words, if I do 15, if I do 89 minus 15 times 2 equals divided by 2, that leaves me 29. This leaves me 29.5 millimeters here, and I need 26, so I'm okay. So all I'm going to tell the carpenter is make it equal, okay? And therefore, now I start with an end, I need 39 for an end distance. I start at 40, and I know that I need at least 52 millimeters, okay, parallel to the grain between these nails. And if I maintain that minimum 52, I'm allowed to put an alternative nail in between, okay? So therefore, I will go to 60. Now, I'm sure that this is wrong because I probably, okay. So that's number 1. Now, what I can do is, of course, I can take my time and start drawing. Okay, I put 3, put 3, put 2, put 2, or you can do it mathematically. It's up to you. Okay, you can do it either graphically and just keep going until you hit the number of nails. In other words, keep doing this pattern until you hit at least 23 nails. Or what you can do, okay, you realize that you start with 3 nails here. You realize that at every 60 millimeters here, you're adding 5 nails in your joint. Okay, so what you're actually doing mathematically, okay, so you need a minimum of, we said minimum of 23 nails. Sorry, 23 nails. This is wrong. Okay, and we're providing at least 5 nails at every 60 millimeters. Okay, so if I take 23 here minus 3, that gives me, I need 4. Okay, in other words, I need to repeat this pattern 4 times in order to have 23 nails. Okay, and therefore repeat 5 nail pattern 4 times, which will give me 20 nails, plus 3, that will give me my 23 nails. So I need to put 23 nails on this side, and therefore the length from here to here would be what? Would be 4 times 60 plus 2 times 40, because don't forget, when you get to the very end, you have to leave the edge distance from the nails to your side plate, which would be another 40 millimeters. Therefore, the total length on this side would be what? It would be 4 times 60, and then 2 times 40, because this is the edge distance here and the edge distance at the other end, which gives me the length of half the plate being 320. And then of course it has to be symmetric. Therefore the total length of the gusset plate, what I would show on the drawing, is a length of 640 millimeters. And that's going to be the size of your gusset plate. And that's all you need to show. In other words, you put the number of nails, okay? You just show a typical pattern. You understand? A typical pattern. And then you don't actually go and do this on each joint. You just show a typical pattern of what you want as an edge distance, okay? And then you just specify the length of the gusset plate, and the carpenter knows that you've provided him enough length for him to be able to put the number of nails that you require for your joints. And you do that for every joint now, okay? So like I said, the 3 rows are gonna work for each member, even the 2x6, because the 2x6, you can probably even put more, but it's up to you. And then after that, if you remember, you put an end distance here, and you remember that if you keep this minimum perpendicular parallel distance here between the nails, you can add, and therefore you go ahead and you do the calculations. So you see, I made a mistake, but it still works out that I have a total of 23 nails, and it works out, and therefore that's it. So that's the last of the design you have to do. In other words, don't forget, like, let's go back just so that we're all on the same page here, okay? So what do we say that our NR value was? Did somebody write it down, please? 0.502 kilonewtons per nail. Is that what we said it was? Huh?
Yes.
Okay, so if we go
Yes.
back here, okay, if we go back here very quickly, okay, here. So if I take this joint here and I divide by 0.502, how many nails do I need for this joint?
$36.
And therefore I need 36 for that joint, okay? And then all I have to do is work out the pattern and make sure I have the right length, you understand? So 5.02, that tells me how many nails I need. And then all you have to do is take that 5.02 now, because that stays a constant, because all your joints are gonna be made with the same lumber, they're gonna be made with the same side plate, and you've calculated the NR value for all those joints to be exactly the same. So therefore this would be 5.52 divided by, and therefore that tells you the number of nails you need for this joint, number of nails you need for, we just did this one, and you would do it for this one here.
And do we give you at the end like the total numbers of nails that we have?
No, what I want to see in your calculation sheet is what you saw here today in the lab for the first one. Then you tell me NR value is the same for all, and then you say for joint number 1 and joint number 2, number of nails required 17.88 divided by 0 is for joint number 3, and you show me how many nails you have, and then you're gonna have to work out for each joint the length of the gusset plates.
So I don't have to add them up like a total number of nails and.
No, like because, and then what you're going to do is that this is just for your calculations, and then after that, based on the number of nails, you'll be able to calculate the length of the gusset plate. Okay, and if you want to see how the gusset plates are, go to those sample drawings I gave you, and you'll see how the gusset plates are going to eventually look like. Understand? So, for example, here, what's going to happen here is this, like the top one here. Okay, you have the top chord here, you have the top chord there. and then you have this member coming in here like this. Okay, some people like to miter the joints. Some people don't even miter. They just leave them straight like that. Okay, so it's up to you. But some people like to miter these members. When you cut something at an angle, it's called mitering. And it's up to you. Okay, so here, for example, okay, the thing is that, you know, this would be very close to, okay, so here, you know that what you're going to do is, so the thing is that you have to determine, where am I going to start my nailing here? Okay. And then, you know, and maintain that spacing. And then once you found that length that you need here, well, that's going to be the size of your gusset plate up to here. And then after that, your gusset plate is basically going to, and then after that, your gusset plate is going to look like this. It's going to go across here like this. And you're going to have your other member in here like this. And your gusset plate is going to go up here like this and like that. And then you're going to, and therefore you're going to have to determine this length here and that length there. Okay. So it's up to, you know, and when it gets to these very geometric shapes, I like what I do with what I do to calculate my gusset plates. I decide where my first row of nails are, and then in AutoCAD I simply offset, 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 and then I let AutoCAD do the calculations for me. Isn't that easy? So use the tools, guys, that you have to simplify your life. You understand? It makes life much easier. So with AutoCAD, you can very easily calculate this size of gusset plate, because once you've established where you're going to be putting these with AutoCAD with those requirements, and you know that what you need, and you just offset with AutoCAD and you'll be able to determine that one. So that's the one at the very top. And you know, and the one like the ones that people have trouble with, like for example, the web member here that goes like this. Well, this is, and here's your top chord. So basically, you know, you just have to calculate the number of nails you need here. Once you've calculated that, you can either do this, flare this out a bit to make sure you have enough room. Okay, and then you put the same number of nails here, and that's going to be that one there. And then where the two of them meet here at the bottom, well, what's going to happen is your gusset plate is going to be having nails there, and therefore you're going to have ample room. And all that's really going to be required is to determine this length here and this height here, and that's it. And that's it. And then your design for your project is 100% complete. And
okay.
Isn't that nice?
Yeah.
See?
Very nice.
And now you guys are going to be able to design your own country place for your parents or for yourselves, and enjoy your living space, as long as it's one story, right?
Okay, so we can't do the double it up. Okay.
Yeah, you can do 2 stories, but you just have to remember the load path and know how the loads are being transferred, because the only thing that changes is the vertical members, or I get more loads as you go down, right?
Okay.
Well, is there any questions?
Because last week you were mentioning about some Excel spreadsheet that you wanted to show us, but we didn't have time.
Yeah,
well, I'm glad you reminded me. I'm glad you reminded me. Okay, so let's do. Do we have time now, or we can do the next slide? Do we have time now?
We have time. We have,
we have
10
time.
minutes.
10 minutes. Wow. Okay.
9 minutes. Oh, like 45 minutes until 6.
I know, but usually, like, what I do is, like, if we were in class physically, instead of taking a 15-minute break and then giving you a 15-minute break at the end of the class, I usually go straight through and give you a half hour, and we all call it a day. You understand? That's how I've always managed it in class, and everybody was in agreement with that. Makes it much more easier, you know. So, anyways, okay. So I'm glad you reminded me. Let me do that right now.
I mean, yeah.
And I'm gonna, as a matter of fact, I'm gonna send you the spreadsheet. Okay. I'm glad you reminded me about this. Let me go and find the spreadsheet. Okay, so here's a spreadsheet. And I just want to talk about this spreadsheet, okay? And unfortunately, I don't think that I'll be able to compare the answers, but okay. Okay, hold on a second. I want to share screen, but this is in the way here. Yeah, like, do any of you have the built-up column tables with all the values for the built-up columns? Like the, you know, like the 2x4s and 2x, or you understand? Does anybody have that table available? Because I can't. I should have
The
brought it up.
table, like,
For the built-up columns, you know, with like, you know, whether you want to use a 2x4, 3-ply, 2-ply, or 2x6, 4-ply, 3-ply, you know, for the exterior walls. Do you have
If
that?
we have it open, yeah.
yeah.
Do you have that table with you? Because I just want to show you. Okay. So I just want to show you the. Because I don't have it, and I should have called it up. Okay, so this is what I prepared for you guys. Okay, now what I want you to keep in mind. Okay, let me just. Oh, first of all, let me close. Does end show. And I apologize for that mistake in the lab, guys. Do you guys see the Excel spreadsheet?
Yeah.
Okay. So what I did here, very quickly, okay, what I did here is, so does anybody have the table?
1 second.
Yeah, I have it, sir.
Okay, you have it. Okay, so now, right now, this is for, like, let's say you're designing the built-up columns. Let me just annotate, okay? Now, what you guys didn't realize, and what I should have highlighted, and I'm going to highlight it now, okay? I'm going to annotate, okay? Right now, all the values in that table are based on the column, the built-up column that you put in your wall here, okay, is not ladder supported in either direction. Do you understand what I'm saying? In other words, you're standing up this column like this, okay? Everybody understand what I'm saying? And therefore, this column can either fail with respect to the B or with respect to D. Everybody understands that? Okay? But in reality, when you're building an exterior wall, what you're actually doing, okay, in reality, what you're actually doing is you're going to have sheeting on the outside of your wall. Do you agree? You're going to have gypsum on the inside of your wall. Do you agree? Okay. Now, if you're going to have gypsum, and if you just have it on one side, doesn't matter, but you can have, okay. And if you are going to be nailing your plywood to your B here, what happens to the B axis? It gets laterally supported. Okay. So what happens is that the table that you have right now, it's as if B is not supported at all. Okay, so therefore, like here, let me give you an example. So Adriano, you have the table, right? Okay. Now, let's say you have, okay, like what I did here for you guys, I'm going to send you this, okay? So for example, if I decide to use 2x4s by 89, okay? And I have a 4-ply column, right? And the length of the column is not supported in either direction, okay? So in the table, Adriano, if you look at a 4-ply 38 by 89 with a length, do you have a length of 2,800 millimeters, or do you only go up to 3,000?
Yeah, we have 2,800.
The PR value right now should be 43.1 in the table, about there, or point.
43.2.
0.2. Okay, so because it's either the rounding up on when they did, okay. Give me a 38 by 140. Give me a number of plies and give me a length.
3 plies. 4
okay,
meters.
let's go to 3 plies. And what length do you want to put in?
4 meters.
4 meters. Okay, both A and B, both D and B are 4 meters, right?
Yeah.
Okay. So the PR value is 23.9.
Exactly the same.
Okay, exactly the same. So in this case, we rounded the same way. Okay. So in other words, guys, when you're out by 0.1 kilonewtons, don't worry about it. Okay. Now, what happens here, okay, is if you actually look at your wall, okay, this is what I want you to understand. Okay. If I look at my wall here, okay. Oh, sorry. I should draw, like I'm going to clear the drawing. I'm just going to draw messy, okay? So for example, here's my built-up column. Okay, here's my built-up column. Here's my built-up column. Now you said a 4-ply, a 3-ply, 4,000 millimeters, right? A 3-ply. So in other words, right now, this is as if this column is standing all by itself, like this, okay? And it has to resist a load, and it's telling you the maximum resistance that it can give you is 23.9. But if this column is part of an exterior wall, you know that in your exterior wall, you are going to put sheeting here. Does everybody understand what I'm saying? You're going to be putting plywood, right? Do you get it?
Right.
And when I'm putting that plywood, and if I nail that plywood at every 300 millimeters, what am I doing to the B of the column?
It's laterally supported.
I'm bringing it down, I'm bringing the LB down to 300, right? LB is no longer 4 meters long, it's only 300 millimeters. You guys understand that? In other words, if this is my plywood here and my column is behind it, my column is behind here, okay? Well, if this is my column and I decide to nail the plywood at every 300 millimeters, I'm laterally supporting the B dimension of my column. Do you see that? Or nobody sees it?
We see
Pardon?
it, sir.
You see it,
sir.
okay? So
Yeah.
therefore, what happens is in reality, when you want to calculate the PR value, if you use the tables, it's as if you're not taking advantage that you have sheeting here. You're just assuming that it's not supported either in the B or in the D. And the tables gives you the value of the weaker axis, okay? But now if I come to my table here and I happen to change this to 300, look what happens to the PR value. It goes up, and it makes sense because now B is laterally supported. So if you want to take advantage of the fact that you have sheeting and that you can laterally support the B and you want to go to the table, then you, instead of relying on a small PR value because B is not laterally supported, you're going to be oversizing your columns if you happen to be nailing it to your sheeting.
So for our project, are we going to be taking advantage of this Excel file?
No, I'm going to send you the Excel file. I want you to have the Excel file. You understand, Alex?
But should we use it within our
If you want,
design?
if you want, I strongly recommend you do. So this way, at least you'll be able to apply it. You understand? It's up to you. Like I'm not going to penalize you if you don't, but I want you to realize. And as a matter of fact, if I'm not mistaken, okay, if I'm not mistaken, I have to go back. And this is, you know, like I'm getting old, guys, so I don't have the same memory, fortunately. And I had a great time in the 70s, so half my brain cells have been burnt out. But that's another story. Anyways, if I'm not mistaken, I think that the standard says that, you know, if I'm not mistaken, and I can go look this up for you, but if I'm not mistaken, but don't do this, okay? If, for example, okay, if, for example, you have a built-up column, okay, and if, and it's not worth doing this, but if you tell, I can maybe find this, but I remember reading this somewhere, and it makes sense to me. Okay, if you, I'm going to change color so you guys can see this. Okay, if you nail each ply, okay, at 300, each ply at 300, you can actually go to the stud table. If you nail each ply at 300, you can actually go to the stud table. You know, the book there where we have the studs, okay? And you can take the value of the PR of one stud and multiply it by 3. If you go through the trouble of doing it, but it's not worth the nailing, you understand? But you can't. Now, just to give you another appreciation is that, for example, when I have a built-up column, it's usually done around windows. We all agree, right? Well, when you make windows, you happen to have a framing here that creates like a sill around your window. You agree? Okay. So this piece of wood also gives you lateral support. So this, you know, but what's really going to give you a lot of the lateral support is the sheeting, you understand? Now, keep in mind, okay, keep in mind that if you have an opening here and you have an opening there, well, you don't have very much lateral support in here. Okay, so therefore you would put this as your LB value for your column. The only time that you'd be able to go down to 300 is if you can put nails all the way down across the column. But for example, if I happen to have my column is here, here's my lintel, and then I was able to frame up to here, and this is all sheeting here, this is all sheeting here. Well, this becomes my LB value. In other words, this is the part of LB which becomes unsupported. And then I would put that there, and I would let my spreadsheet calculate the PR value. And it'd still be better than just going straight to the table and taking an LB going the full length or the full height of your wall. Okay, so I will send you this spreadsheet. Send, I'm gonna write it down, send spreadsheet. So, and guys, that's where, see, like, that's why, like, as a matter of fact, when I did the spreadsheet, okay, I compared my answer. Well, first of all, I did the spreadsheet, and I did a couple of manual calculations, okay? And then after that, once I finished my spreadsheet, I took a couple of values in the table and I checked them, and I noticed that it was either we were exactly had the same value, or I had, for example, 1.1 kilonewton more, or they had 1.1 kilonewton more. And I guess it all depends on when the guy did the calculations for the spreadsheet to how many decimal places, because you know Excel, when it comes to calculating, I think Excel goes to 16 decimal places. So you know what I mean? Anyway, so I have more confidence in my spreadsheet because I won't make the mistake I made in the lab where I go to the table and take the wrong value in the table. Here, when I know that I'm using a 3-ply, and I know that I have, you know, this is for all dry condition, you know, like dry everything. In other words, this is where, and all that, and this is where the value that you have from that. So in other words, when I know I have a dry condition, standard load, like in other words, a typical exterior wall, well, this is what I do. I would rather create myself an Excel spreadsheet and then use the sheet to go and get the values of PR, because I can rely on these totally, understand? So this equation here is basically, and of course, okay, and the reason why, and here guys, the reason why you don't, like, for example, if I remember when we did the bearing walls and all that, okay, remember I told you that just so you guys can appreciate is that when we did the bearing walls, we started off by saying, okay, we looked at the bearing walls and we said, okay, we're going to have some blocking here on the bearing walls. Okay, and therefore it's going to change the value of LB, and therefore you compare the slenderness ratio of LD with the slenderness ratio of LB, and the higher slenderness ratio is the one that's going to govern. And then so you either calculate PR based on the highest slenderness ratio. Is it going to be the D that fails, or is it going to be the B? The reason why you can't do this here is because if you look at the equations, this side here gets multiplied by 0.6 for the PR because it's a built-up column, and that changes everything. Okay, so this is the big difference for built-up columns. Like when we're doing studs, here you had PRD is exactly the same equation, and here you had and this wasn't there when you did the studs. Whereas for built-up columns, they reduced the B because it's nailed here. They reduced it by 40%, and that's why you can't do it that way. So all I did is I put the two equations here, and I didn't bother calculating the slenderness ratio. I let them calculate both, and then this is my argument here. If you look at this argument here, it takes the smaller of these two values here, and it tells me, like, so for example, once I change this to 300, it gave me a PR here of 89.5. Here it gave me 51.5. Therefore, it's the D value that's going to buckle, and therefore that's my PR value. And that's what I like to do. I like to use technology to simplify my life, and not only that, to make sure I can minimize making mistakes, guys. Okay, and that's the most important thing I want to stress to you guys when you're working career. Try to minimize, like, guys, you're always going to, I made mistakes today in my lab. Okay, we all going to make mistakes. Just try to minimize them, please. Okay, so I'll send you the spreadsheet so you guys can have this, but it's not hard to do. You understand? Like, it's not hard to do. And I'll send you the spreadsheet, you'll have it. And if you want to use it for your project, so therefore, if you want to now calculate your PR value, you know, like for the columns as opposed to taking the values in the table, well, this would be a good way of doing it, you understand? Because I can tell you that, for example, if you don't use the spreadsheet, I can tell you right now, your columns are all going to be 3-ply in your project. Okay, but if you take advantage of the spreadsheet, you can make certain columns 2-ply. Sounds good? So who's the one that reminded me to show you the spreadsheet?
That was me.
Thank you very much, sir. Okay, appreciate
Maxime.
it. Okay. Maxime, I appreciate it. And I hope you guys appreciate I put these things together for you to simplify your life a bit. That's what I hope you appreciate. But so, okay, guys, so that's basically it. So I will send you the spreadsheet and you can use it for your project. And I know some of you will, some of you won't, but like it's up to you on how much you want to learn and, and how efficient you want to be when it comes to, doing certain designs. It's up to you. I will not penalize you wrong if you do it the other way. If you end up with 3-ply all the way around, I'll mark it right because that's, that's the conservative way of doing it. How can I mark it wrong if 2-plies is sufficient and you put 3-plies? How can I mark that wrong? 3-plies is even more right than 2-plies in terms of strength. So how can I mark that wrong? You see? And that's why I can't mark it wrong. But if you're really looking at, if I was supposed to mark you on optimization and refining your design and all that, yes, then I could say you could have gone this way if you wanted to. You understand? As a matter of fact, there's one thing I hate that I read in the new Engineering Act. Okay, apparently, and I don't know what kind of turmoil this is going to cause in the profession, but apparently there was one term that I wasn't too crazy about. And I can tell you guys, I am so happy that I am at the end of my career. Because it almost looks like if you don't optimize your design and if your client, it almost sounded as if you don't optimize your design and your client is overpaying to have the work done, he can probably sue you for not doing your job as an engineer. That's what it sounded like when I read the law, and I think that that's really stupid. Understand? But I wasn't there to write the law, and but I can tell you that I wasn't too crazy about that, and I don't know what the ramifications are going to be with regards to that, and I'm pretty sure that it's going to open up. It should open up a can of worms somewhere. Some conservative engineer that's going to feel not too comfortable doing things right to the bone. He's going to do a little bit thicker, and all of a sudden you get this developer that spent an extra $3,000 on his reinforcing steel for a 20-story high rise. He'll sue him for that extra $3,000 of steel. That's what I think is going to happen. And like I said, I find that's really stupid. And whoever was on the committee to develop that law was really short-sighted when it came to that. Anyways. So guys, that's going to be something, those of you that are going to get into the engineering and you're going to get onto the consulting side where you're going to be doing a lot of design. I don't care whether it's structural design or, foundation design, all that. It's going to apply to all engineering, you understand? Not only the structures, it's going to apply to all engineering, and it might have certain consequences. So you guys will let me know when I'm old. Well, I'm already gray when I have no more marbles, and you'll let me know if I was right in what's going to happen about 5-10 years from now when it comes to engineers that do not optimize their design. And on that note, thank you for giving me this extra 10 minutes. So guys, from here on end, the labs, I'm just going to come. I'm going to have the lab period, you understand? And I'm going to answer questions. And if you don't have any questions, well, we're just going to call it a day, and then you guys are going to be able to work on your lab. And from here on end, if you have any questions, hold on to it. I'll answer them in the steel lab. Even if it's a wood question, I'll answer it in the steel lab. And even if it's a steel question, I'll answer during the wood lab. So I'll answer any question in any lab at any time. Just hold on to your question. And this way, the questions you have, maybe half your classmates might have the same question. So it's good that we all get to see exactly what it is that you need to overcome. Sounds good?
Sir, I have a question, but it's not related to the project.
Okay.
For the lintels, I was looking at my construction detail, and there's insulation between the two pieces of wood for the lintel. Is that common?
The architect would specify that.
Because when we designed it, it was just like one built up.
Yeah, exactly. See, that is not your concern.
Okay.
You follow what I'm saying? See, when it comes to the envelope, Alex, okay, the architect, first of all, I believe it was in, hold on a second, I'm going back, okay. You guys weren't even born then, okay, but what happened was is that the price of oil went through the roof, okay? And all of a sudden, energy became very, very expensive, okay? So what the government did is that they legislated an act, a law, okay, regarding energy conservation when it comes to buildings, okay? And what they did is they said all buildings being built as of, let's say, 1984, the thermal resistance of the wall has to be so much, the thermal resistance of the ceilings have to be so much, the thermal resistance of the foundations have to be so much, and so on and so on, okay? So there's all these criteria that the architect has to conform to in order to respect the requirements of that law. And he's the one that is responsible for the envelope. The envelope is all the insulation, all the cladding, and all the finishes. He doesn't care whether it's a 2x6, he doesn't care whether it's a 2x10. He just has to worry about, okay, how much insulation can he stick in here? Okay, so for example, if all of a sudden, like 3 pieces of 2x10 to make your lintel, if the thermal resistance here doesn't give him, and then the little bit of insulation that he can put here on the inside, okay, if he doesn't get his whatever it is, I don't know what it is because I'm not an architect, and I never go and prance around in the field of an architect, but let's say that this happens to be in imperial, I don't even know what it is in metric, but in imperial, this happens to be R20, okay, well, the architect would tell you, we need to make sure that your lintels, or he would have to break his head on how to make this to be an R20. You
So
see?
he wouldn't tell us, like, let's say this is not sufficient, we need more room. He would just, the architect would do it himself.
Well, no, then you would work, you would work jointly with the architect, Alex. You
Okay,
understand?
got
Like
it.
in other words, like, you know, it's a team effort. You know what I mean?
Got it.
What,
Okay.
what I'm getting at is that if all of a sudden if I, for example, here's my truss sitting on top of my lintel, you understand? And I calculate my loads. I need 3 2x10s to support that load. That's all I care from my point of view. You understand?
Yeah.
Now, after that, if he says, yeah, but I need to create an R value, so we'll work out a solution. You understand?
Okay, got it.
You know, so if, for example, if it's better for him, like, for example, if this lumber doesn't work and he needs to create something, you know, Alex, I can tell you that, well, in that case, I might decide to build up what we call, you know, a box beam with plywood, you understand? And then build up a box beam with plywood and see, and calculate and then fill this in with insulation and see if that works for him. You understand? Like I would try to find him alternatives, but that's not my concern. You understand?
Yeah.
And then if all of a sudden he says, well, I need to have so much insulation, well, put it here and create a bulkhead, you know, if you want to be, you know. So, but it's nice to work out solutions with the architects if you can. And these guys will give you alternatives, and then all you have to do is calculate to see if it works. You understand?
Okay, sounds
So
good.
I know what you're saying. Like, so that insulation in between is nothing for you and I. For us in engineering, you understand?
I was just wondering if in your design process, if that's something that we should always account for within our lintels, if we should make sure that, like, the middle there's a gap, or.
Well, what I'm getting at is that, for example, let's say that you're going to be designing the whole house without an architect. Let's say you want to go that way. Then you better make sure the whole house is designed properly.
Okay.
You follow what I'm saying?
Got it. Yeah.
But I don't recommend you do that. You understand? Because why do you want to wear so many hats? Wear one and make sure you wear it properly.
Okay. Yeah.
Does that make sense?
Yeah, it makes total sense.
Okay. And that's where a lot of people, like, I don't understand what they're like. I could understand in construction one giving you the general overview of a building and making you understand there are different components, but I would stress on what is our domain, what is their domain. So you guys can separate, well, okay, I know that this is the building envelope, but it's not my domain. You follow? They teach you construction one, and they don't teach you how to separate the responsibility when it comes to that component in the building.
That would be like interesting to know.
Pardon?
That would be like a good, like, interesting thing to know, like your oversight of it.
Well, I mean, exactly. Like, so if I would be teaching construction one, yeah, you learn about vapor barriers, you learn about insulation, you learn about this, you learn about that. But then I would tell you that all of this is not your problem, unless you take it upon yourself to make it your problem. And then at that, you know, that's, so I would stress what becomes your responsibility and what becomes the responsibility of the architect or the architectural technologist. You understand?
So, sir, for example, like, let's say there was an architect that designed the house, okay?
Okay.
And would you be, and there's a civil engineer that's obviously appointed on site to build a house, right? In charge, like the project manager.
Okay.
So, like, the architect's responsibilities would be, like, what would be what, for example, like you're talking about, like, what would be the project
Okay, so
manager's
in other
responsibilities?
words, okay, so see here, like now we're starting to break down the fields of responsibility. Okay, so number one, if the architect, okay, if the architect designed the house completely, okay, but he was not coming to the site at all, so he's got no supervision.
Okay.
Okay, so let's take that scenario, because this is why there's not one answer. It all depends on the scenarios. So let's take the scenario, the architect designs the house totally, okay, and you're the project engineer and you're a structural engineer, right? And you build it exactly the way the architect designed it, okay? And there's a problem. The roof leaks, or there's not enough insulation. The guy comes with a thermal camera. There's a problem with his design. Well, he's going to have to answer to it, not you. It's a design problem. Now, let's say that he designed it properly and you didn't realize that the guy that was doing the installation, well, he cut a couple of corners and he didn't do it properly. And all of a sudden it's leaking because it wasn't done properly. Well, the architect's not responsible. You are responsible because you're in charge of the execution.
Okay.
You follow?
Yeah.
So that's where you separate, you understand? So, and as a matter of fact, I can tell you this, guys, this is okay. There was a project, okay. They had a job meeting, and guys, when I heard this, the results of this, I fell at the bottom of my chair, okay. There was this project, and they had a job meeting, okay, and there was a whole bunch of people. So in other words, they must have been, you know, like at the stage where the roofer was there, the roofing subcontractor, the architect, the structural engineer, a big site meeting, okay, that this happens once every week. And at that meeting, okay, they were discussing the roof, and the roofers told the architect at the meeting, and it was written down in the minutes, okay, he said, well, if I build the roof the way you designed it, it's not going to work. So the architect huffed and puffed and says, what do you know? I designed it that way. I want you to build it that way. And that's it. So the roofer says, okay, at least I brought it up. Okay. They went ahead. They built the roof exactly the way the architect wanted it. And sure enough, guess what happened? It leaked. Okay. So it was a big thing. Everybody got sued. The contractor, the subcontractor, the architect, blah, blah, blah. Okay. And then all of a sudden they went to court. And guess who the judge condemned for the leaking roof? The roofer. Would you believe? Why? Because when he admitted that he knew that there was going to be a problem, he should never have gone ahead and done it anyways. He should have insisted that he wouldn't do the roof. And he got the one that was condemned for the architect's problem. So the moral of the story is, when you're like, you keep your mouth shut. You follow? And this now becomes jurisprudence, and that's the law. So the roofer, he thought he was doing a good thing. He thought he was, trying to help the architect out. And then, so, it was like saying, well, if you knew that the roof wasn't going to work, you shouldn't have built it in the first place. And he's the one that got condemned for paying all the damages. And I found that really sad. But that's how that judge interpreted the situation. And that's why I keep telling you guys, even if common sense tells you that it doesn't make sense, well, there's a lot of judgments out there that, to me, that don't make sense. Okay, but mind you, I'm not a lawyer. I don't know the philosophy of law, and therefore I can be totally wrong. But when I heard that judgment, I felt like I was taken back so much. Okay, so Adriano, like I said, the architect is responsible for his design. If he happens to come to the site and he's also supervising partially with you, and something goes wrong, he's responsible then. But if he never comes to the site, you're responsible if it's an execution problem. But if he has a supervision, if something goes wrong, he's responsible. Okay. And then again, it depends on what kind of supervision mandate he has. Okay. And that's in a way fair, because some clients don't want to pay for full supervision. They only pay for, you come once in a while, and therefore once in a while I can only see a few things here and there. And when I come, and that's it. So I found that judgment was pretty fair when the when the judge ruled in that favor of the architect, saying the client gave him a partial supervision, you can only expect a certain partial quality control from that type of mandate, and therefore he didn't hold the architect responsible. And that was really good for the architect. So this way clients will realize either you pay for the service and you get a full service. If you want to pay for a partial service, I'm gonna have partial responsibility. So that then it falls into the hands of the anyways, guys, best thing to do is to avoid mistakes. That's the first thing. And then after that, if the mistakes are made, hopefully nobody got hurt. It's just money. And then after that, go on with your life. You understand? And on that note, I'm going to clear this drawing. Stop sharing. So I hope you enjoyed today's lecture, guys. And I apologize again for those little typos in the lab. And we'll talk to you guys on Monday, right?
On Monday,
Thank
sir.
you, sir.
Thank you.
Okay, guys. Talk to you on Monday. Bye-bye.
Bye, sir.
Bye-bye, guys.
Thank you.
You're welcome. You're welcome.